Alright, let's go. So, pretty simple today as well. Pretty simple. We're going to do a Leetcode problem after I do one monkey type, and then I'll try and limit that Leetcode problem to around 30 minutes to an hour, and then I'll do some exam revision. And then later on in the day I'll also be headed to the gym, so all pretty average stuff to get done. One more. Oh, hello you guys. Welcome to the stream. Oh, you have an interview tomorrow. Oh, good luck for that, Manus. And hello Zahib, hello Nafis. Whoops. Negative 1 0 3 div 2 nope damn bro, this is I hate this specific question that they have here, because you're doing repeated actions. Let's see, d space percent d space percent d space percent d, array of 0, array of 1, array of 2, array of 3, return 0. Okay. Do this using your Mac keyboard. It'll probably take longer. But Manas, no worries, man. Zahib, you're learning 10-figure typing as well, and bro, it's really difficult. Like the lower row is super difficult. If you're doing 10-figure typing, let's have a look, right? This is my keyboard. Um, 34 words per minute on Go. Use my Logitech Ergo 1. I see. Yeah. My highest was like 50 word per minute. C++ on monkeytype. God damn. Typing race. I'll have a look at it in a moment. I'll just do one more of this, just the same one on this keyboard. Oh, the problem is, look, I'm looking down at my keyboard because I don't know where some of these keys are. I feel like, so before it was a 20 word per minute, but I did stop midway. Can I beat that? See, look, I'm looking down at my keyboard way too often. %d, %d, %d. The thing is, I have to move my hand a lot more with this. Return 0. Yeah, 33 word per minute, not bad. If you're talking about type racer, I've used type racer before for sure. No. Yay! But I'm beating guests. I do have an account for this. Login failed, too many requests. Hello? Yes, 67 only. Yeah. One, 4. But some parts of the world, like the Sherry region in Spain and the Port region in Portugal, have made quite a specialty of... Oh, I'm falling behind. Dessert wine is the legal U.S. terminology for these wines, probably because they are usually sweet and often enjoyed okay. Damn, didn't make it. Couldn't do it, man. I came last. I choked a bit, to be honest. Alright, let's do Leetcode problem. Now, we can finish heap queue if we just do one right now, or we can do something else. Now, a design Twitter. Wow, okay. Should I do it? I'll do it. Design Twitter. Oh, this is another one of these. I don't want to do another one of these init functions. I just want to do a normal one. So I'm going to just do a trie problem. We'll say blind75's trie problem. Oh, they're all okay. Just the same thing. Damn it. This is also similar. This is is also just defined as an init. Oh, it's alright, I'll just do this. Obsidian. We're gonna call this implement prefix tree. Implement prefix tree. Now I'm gonna say try and limit myself to at most 10 minutes to solve this problem. If I can't figure it out, then I'm gonna look at the solution. So we're gonna just set a stopwatch or set a timer for how long is the solution? 18 minutes. Okay, so if it's 18 minutes, I'll say give myself 12 minutes here, and we'll just go. Okay, a prefix tree, also known as a trie, is a data structure used to efficiently store or retrieve keys in a set of strings. Some applications of this data structure include autocomplete and spell checker systems. Interesting. Implement the prefix tree class, where the prefix tree initializes the prefix tree object, inserts the string word into the prefix tree, returns true if the string word is the prefix tree was inserted before, or false otherwise. Boolean starts with returns true if there is a previously inserted string and that the prefix blah blah blah. Example is if you have tree, insert dog, search do, starts with do, insert do, search do. Okay, output is this, and this is the explanation. You would return some values. Okay, implement prefix tree, sure. Hello, Verlius. Two of the functions have the same code in that. What, in this problem? Okay. Maybe I'll keep a note, but okay. So a prefix tree, also known as a trie. Okay. So this is a trie, is a data structure used to efficiently store and retrieve keys in a set of strings. Efficiently store and retrieve keys in a set of strings. Some applications of this data structure include autocomplete and spell checker. Implement the prefix tree class, which is, so prefix tree initializes the prefix tree object, or whatever that would be, whatever that entails. The void insert with a word inserts the string word into the prefix tree, sure. The Boolean search string word returns true if the string word is in the prefix tree, i.e. was inserted before, and false otherwise. And Boolean starts with returns true if there is previously inserted string word that has the prefix, and false otherwise. So this all makes sense so far. So if you got a tree, you initialize the tree. Insert, you insert dog. Search for dog, that should be true. Search for do, that should be false. Search for, or starts with do, it should return true. Insert do, that should return, or when you search, then it'll return true. And okay, so how could you potentially even think about this problem, right? What is a tree? What is a trie? Okay, so that's gonna be tough. How could a trie work here? Exactly. And what is a trie? So let's have a quick read on what a trie is. Trie, W3 schools maybe. So a trie data structure, alright, is a tree-like data structure used for storing a dynamic set of strings. It is commonly used for efficient retrieval and storage of keys in a large data set. The structure supports operations such as insert, search, and deletion of keys, making it a valuable tool in fields like computer science and informational retrieval. In this article, we go and explore the insertion and search operations in the trie data structure. So insertion and search are both the operations that we are concerned with in this problem as well. So this is going to be also where I learn trie. Okay, so representing one of the tries, so let me write this here. We're going to say trie. Okay, trie. It's not necessarily a binary true, is it? Or is it? Nah. Representation of a trie node, insertion in a trie data structure, searching in a trie data structure, implementation of search and trie and search and insert ops in trie, and complexity analysis of trie. So representation of a trie node. A trie data structure consists of nodes connected by edges. Each node represents a character or part of a string. Okay, the root node, the starting point of the trie, represents an empty string. Starting node of a trie represents an empty string. Each edge enumerating from a node signifies a specific character. The path from the root to a node represents the prefix of a string stored in the trie. Okay. A simple structure to represent nodes for the English alphabet can be as follows, where you have a trie of 26. You have the ending of a string, trie node, word end is false. Initialize the word end variables. Initialize every index of a trie node array with null. Am I convinced? This is in C++, so we can do it in C, alright, yeah, fair enough. Oh, C++. Yeah, I'm just reading it. Insertion in trie data structure. Java. Python. Jesus, Python, gee, why is it so small? Word length. Word end, okay. Right, for sure. I think I can understand. So this is a struct, so okay, so this is struct. Okay, I mean, I like looking at these different language alternatives because that's actually pretty cool. I will say though, C, can I make sense of C right now? Because I haven't done it in a while. The malloc for sure is something that I haven't need to remember. The malloc size of the struct of tree node. Love it, love it. And this is the address, or this is the pointed. Yeah, the node is pointed to right now, or something. Yeah, something like that. All right. Yeah, okay, regardless, Python. So insertion in trie data structure. Insert, so let's walk through the process of inserting a word into a trie data structure. We've already covered the basics of trie and its node structure. Here's a visual representation of inserting the word and an ant. And an ant. Yeah, for sure. This is what I was thinking in my head as well. So inserting and starts at the root. The root has no character associated with it, and it's a word and visits. Word and value is 0, indicating no complete word ends at this point. Okay, word ends. No completed word ends. Right, can I make sense of that? That's a trie node. No completed word ends. Okay, sure. So first character A. So index A. Calculate the index using A minus A equals 0. Check the child 0 is null. Since it is, create a new trie node with the character A word set to 0 and empty array pointers move to the new node. N minus A is 13. Check for child 13. Ooh. Okay, so Yeah, I can see how you use an array representation here to represent everything, but check if this is null. It is, so this is what exactly? Just child, okay. So create a new trie node with n empty array pointers, move the new trie node. So calculate the index using d minus a to 3, check if child 3 is null. Let's create a new trie node. Set 1, indicate the word and indicating the word and ends here. So word end, so create a new trie node with the character d, word end set to 1. So word end set to 0 and then empty array pointers. Yeah, you set it to 1, indicating word and has an end here. So once you reach the end, well, what's that? You look to the next one, perhaps? Or you just mark the node as, yeah, word end, which is fine. Okay, start the root node. It doesn't contain any data, but it's keep tracks of its every first character of every string that has been inserted. So first you find that it is null. We already have a node created, so move to the next existing a node. So move to the existing a node. First character n, calculate n minus a, check for child 13. Check if child 13 is null. If not, move to the existing n node and calculate the index using t minus a, 19, and yeah, okay. So if that's insertion, that's pretty straightforward. I am pretty good with. So minus says, do you know about trie? So this, I'm just learning about it now, pretty much. Yeah, malloc PDSD. Yeah. Trie is an n-ary tree. Basically, every node has a suppose in this case 26 nodes. Each node is representing an alphabet, and you can add other features as well, like boolean, end of word to solve. Yeah. So this is actually pretty nice. Yeah. So looking at this all makes sense so far. Now, you know, this trie thing, this trie idea is that you'd have a fixed number of or inputs, or in this case 26 letters, right? And you know, this reminds me of the problem that I had with, you know, the graph problem that I had. So I had this graph problem in my Amazon interview, and now looking back, well, let me turn that off. Now looking back, that wasn't really a trie problem then, perhaps, because I'm using a list. And maybe it is still a trie problem, but it's not, I don't know. We'll see more examples here, but searching in a trie data structure is probably pretty straightforward. You just keep looking down the trees, so I think I'm fine with that. So look, time's up. We have learned now a little about the trie in general. So first off, let's put down this as something we learn about. So learned about the trie data structure. Now the trie data structure. Insert and search Geeks for Geeks. I did it on Geeks for Geeks and not W3 Schools. That's fine, I guess. And the problem itself, we are just going to copy. But and you can access each node with character minus a if all characters are small. That's it. Yeah, if all characters are lowercase. Yeah, I knew about that trick, so that's pretty good. Now, if that's the case, right, I kind of want to spend another, what, 15 minutes to try and write this out and see what I can do with it, okay? So I will write it out, all right? After reading that, I think I can understand how to write it out. It'll just mean that I'm going to give myself another timer of 15 minutes, but instead of 15, I'll make it 10, perhaps. See how fast I can do it in 10, or if any. All right, so we'll say 10 minutes. Keep track of the time, and we'll see. Init. So we init by I guess we need the class of the node, which consists of some child, and since they're all lowercase letters in this case, we can say self the node here. So I think I can get away with, this is just Python syntax at this point that I'm forgetting exactly how it works, but you can possibly say 0 to now is it 0? We'll say none to 26, so none times 26, and we're going to say this tree node is word end is equal to false at the beginning. Cool, and we init by saying we create a node. Now we can say it's a trie node, right? So maybe I'll keep it to a trie node, call it a trie node, and a trie node takes as input self maybe. I feel like that's not entirely right. I feel like if I create this into a data class, that might be better, but also I don't know if I'm really taking the right approach here. Data class, and I forget which, I'm just going to quickly check, fuck it. Were Alacrity. Let me open up Alacrity, go to Signal Protocol, because I did do this with the Signal Protocol, and we're just going to open it up in VS Code. And how did I do with data class in Python? I just legit put the value. Okay. Yeah, okay. Let me close that again. So this is literally it. So then trie node gets created, which originally has no value in it. There's nothing in it, so yeah, that's fine, I guess. Insert, we insert a word, so the word for letter in word, letter has to be added to the word, but we know we're going to have to do some OR operations, so OR of A, I think, and OR of L, so that's the letter, minus OR of A. So this is just going to be the index by which we add this child. And this is just going to equal to some trie node of, now it's going to equal to some trie node where the trie node child, okay, node is equal to trie node dot child okay, self trie node is equal to this. I guess you can call this root. Sneeze. Child of the self.root. Okay. The node child, do I need to ever change? No. I see, and it's all encoded in the child. Okay. Node is equal to self.root, and this self.root is just going to be node. We're going to say node is equal to node.child. So this is a list, right? We'll just say ord L minus ord A. And node for search. Start from the root. For L in word, ord L minus ord A. With some sort of node child, this is equal to node. Now, so I never finished this because I need to say, okay, so I'm going to change this to I, and then for range len of word, node, yikes. I need to consider this a little harder. But I'm on my way, and I'm not going to finish it on time, I reckon, in the 2 minutes that I have left. But I'm on my way thinking about it. So back to insert for a second. If you got a node to be the self root, and then you say, okay, I in range of len of word, node child. This node's child is going to be a new tree node. Okay, if node.child ord L minus ord A is gonna equal to none, then you would do this. Else you would just let this equal to that. So this ensures trie node exists. I'll just call it a node. Ensure node exists. Move to next node. Now the child trie node. Yeah, no, I can't get it all done. Alright, well. Okay. That was in 10 minutes. This is how much I've written in 10 minutes. I can solve it, I think, I'm pretty sure. So we'll just spend another 5. Alright, we'll see. So new node, trie node, new node dot word end is equal to true. Or is it this node's word end? Let me think, is it the next node's word end or this node's word end? Ugh. There's a lot more implementation specific issues that I gotta consider as well. Alright, let's just look at the solutions. We're fine. We spent 25 minutes
here. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve implement trie, aka a prefix tree. So a trie or a prefix tree is a special type of tree, and it's used to efficiently store strings. And the applications are some stuff like autocomplete and spell checker. The reason is because the prefix tree allows you to efficiently filter and search based on prefixes. So let's look at the actual implementation of it. So we're going to have an object. That's what we're going to be doing this time, a trie object. And our job is to fill in 3 functions. The first function is going to be inserting a word into the trie. The second function is going to be searching for a word in the trie to see if the word exists. And the third function is going to be to check if there is a word that starts with a given prefix. So those are the 3 functions we're going to do. And let me just go through the rest of this explanation, and then I'll show you what a trie actually is. So here you can see basically what we're going to actually be doing. They're going to be instantiating the trie, right? We're going to be inserting a word such as apple, right? Then we're going to run search. Does the word apple exist? Well, we just
how are researchers going to hire you soon?
We're going to return true.
How
apple
so?
Exists.
How
then
so,
we're going to
my
check,
guy?
does the word app exist? It does not. The word app does not exist.
Nah,
and third, we're going to try starts with app. Are there any words that start with app? And answer is yes, so we return true. Remember, apple starts with app, so we return true. The prefix, right? This is the prefix. App is the prefix of apple. So now let me show you the actual data structure. So let me show you what a trie is. And in this problem, they told us that the limitation is that the words are going to only have characters from lowercase a to z, right? So this is lowercase a to z. So that means we're going to have exactly 26 characters to worry about, right? But so this is a tree, right? It's a prefix tree. It's a special kind of tree. So initially our tree is going to be empty, right? But let's say we want to insert apple. So if we want to insert the word apple, how can we do that? Well, this is what we're going to do. We're going to create a node for the lowercase letter a, right? Then we're going to create another node for the lowercase letter p. And we're going to basically keep doing this for every character in the word that we're inserting, right? We're going to say A, insert it, P, insert it, second P, keep doing that. And every time we're inserting a new character, we're going to add it as a child of the previous character. So we inserted the word apple, right? We can clearly see that. One more thing we have to do to say that this is the word that we inserted is we have to mark the end of the word, right? So this is the end of the word, right? The letter E is the end of the word. So we're going to mark it such that so that this is identified as the end of the word, right? Not, for example, this, right? If we mark this as the end of the word, then we're basically saying we inserted the word AP. But we know we actually did apple, right? Full on apple. This is the last character, so we mark here as the last character. We are marking it even though it's kind of self-explanatory because this character E does not have any children. It's basically obvious that this is the end of the word, but we're still marking it just to be safe.
Just to be safe.
So you can kind of see what we're doing here now, right? This is kind of the root, right? So really what's going to be possible is we have 26 characters, right? So
Why is it
potentially
just to
we
be
could
safe?
have a node at the first layer for every character, right? So A, B, C, D, etc., right? We could have a node for each of these, basically indicating that here is where we're going to put all of the words that start with a B. Here we're going to put all the words that start with a C. Here's where we're going to put all the words starting with D.
Agreed.
So the next thing we're going to do is run search. We're searching for the word apple. So how are we going to do that? Well, we're going to start here at our root, right? This is technically our root, even though it doesn't really have a character, right? So that's basically just a placeholder.
I gotta realize that that's a root. So the node child of this one word specifically now. I should also say, we're gonna just use index. So index, I might call it IDX, is equal to ord of word I minus ord of A. Right, just have this like that, so that we don't need all of what's inside the brackets. Whoops. CI bracket word, sorry, IDX CI W too quick, CI bracket IDX CI bracket CI bracket CI bracket IDX. Okay. Now that means, okay, if ensure node exists, if node child IDX is equal to none, the node root child node is equal to none, so then you create a new node, and on this new node, for this IDX, node word end is true only if I is equal to len of word minus 1 and then the child node move to the next node. So I think that would work. No wait, if no word end, move to the next node. Doesn't matter, it would be none. So it doesn't matter. Doesn't matter when this happens. So I think we can leave it as is when you move to the next node. I feel like this should be done in a while loop better. But whatever.
Node, right? It doesn't have any characters, but it's considered the root, right? And so we're going to check, does this root have the child of the first character that we're looking for, right? So take a look. This is the word we're looking for. Obviously, we're looking for the character A. So we check, hey, there's the A, lowercase a, right? It's the first character of the word. That's what we're looking for. Great. Now, for this A, we're looking for the next character, right? So does this A have a child P character? It has exactly that. So we do have this P, right? And this is what we're doing, right? We're going character by character in the word we're searching for and checking if a node exists for each character consecutively, right? As a child. So next character P, does this have a child P? Yes, it does. Next character L, we have a child L. Next character E, this is the last character, so we do have an E over here, right? And last thing that we have to confirm is, okay, this is the last character, is it marked such that this is the end of the word? Is it marked as if it was the end of the word? It's blue, right? That's what we're doing to indicate that it's the end of the word. So it is, right? So clearly we do have apple. We search for apple. What do? We return true because apple does exist
so that's why
in the
we
trie.
need it.
So next, let's
right?
run search.
Why do we need it? Because if it's a apple, but then you have, say, apples also inserted, then when you search it, you need to ensure that you know apple is an end of a word by having that end of word. Or else, if you assume that it's only the next node, then you almost overwrite the existence of apple. So you need apple if you put in apples. Sorry, you need the word end if you have apple and then directly after put apples. Okay, understood. But yeah, no, that's right.
Again, and this time let's check if a word app exists inside of our trie. App, right? Not apple. So obviously we know that starting from the root again, we do have a lowercase a, just like we checked. We do have a lowercase p after that, and we do have a second lowercase p. So since we do have all three of these characters, right, a, p, p, shouldn't this function return true? No, we're not returning true, and the reason is this node is the last character of the word, right, p, and it's not marked blue, meaning it's not marked as a word, right? Remember, we only inserted apple into our trie, right, into our tree, and we marked this as the end of the word. We never inserted app into the tree, so this is not marked as the end of the word. So we return false for saying that app does not exist in our tree. App is not a word yet. Next, let's run another function on our tree or trie. We're going to check, does a word start with app? How can we check if a word starts with app? Well, we're basically running the exact same thing what we've done, right? We're starting at the root. We're going to check character by character. So this is pretty, like all three of these functions are pretty similar, right? We're checking character by character for all of them.
Yeah,
start at A,
pretty similar.
A exists, check P, P exists, check another P, P does exist. So since we found all of the characters, right, we're basically guaranteed that either this is a word itself, which clearly it's not, right? We never inserted app, or we're guaranteed that there is some word below that has been marked, right? Because if we inserted these characters, we only did that because we were inserting a word, so there's guaranteed to be at least something that is marked blue down here, right? So once we found this character, the second P, which is all the characters in here, then we can say true, right? There definitely exists a word that starts with app, right? And so this starts with function is the main reason we're even implementing a trie in the first place. Because if we want to insert words and search for words exists, right, to check if a word exists, we could just use a hash map for that, right? Because hash maps can, or hash sets can do both of those things in O of one time, right? But this is really the problem. Starts with, it allows us to check prefixes, right? So now let's say we were inserting another word. Let's say we're inserting the word ape, right? A-P-E. How are we going to do that, right? We're inserting another word. What does that mean? Are we going to say A-P-E and then just create a separate node for each of these as children, right? And just connect them such as that, right? This is a child of A. This is the child of P. Are we going to do that? No, because we could reuse it, right?
Tries are actually pretty nice. Damn.
A's in the first position when we already have an A over here. So if we are inserting this word ape, we're going to leverage this A that we already created. Great. And then we're adding the second character, P. We're going to leverage this P that we already created. And so we've inserted the first two characters. What about the last character, the E? Do we have an E over here? No, right? There's no E in the third position. So what are we going to do? We're going to create another child node, right? Now we create an E, and last but not least, we mark that this is the end of a word. So
Alright, resume,
So
sorry
you
about
can
that.
see that a trie actually has the potential to be pretty efficient because we are reusing a lot of nodes, right? We're not necessarily creating a separate node for every single word. Now let me just show you one last thing before we jump into the code. So we're going to do one last function. We want to check, does any word start with B? And I'm just illustrating why we're even implementing a trie in the first place. It's because the starts with function is very efficient compared to other data structures. So for example, let's say we had a list of words, a list of strings, and let's say the size of that list was equal to 1,000,000, right? How long would it take for us to check if any word starts with B? Worst case, we would have to check every single word in the list and check if it starts with B. And what if there was 0 words that started with B? Then every time we would have to go through that entire list of 1,000,000 words. But with a trie, like we've implemented right now, it's very efficient. Here you can see we have two words, right? We have one word here and we have a second word here. And it's possible we could have 1,000,000 other words, right? Like clearly there's probably a lot of words that start with the character A and maybe so on. But when we run this function,
I mean, a trie is pretty foundational, isn't it, I guess?
Starting at the root, we're checking, do we have any children with the character B, right? We check this first layer. How large is that first layer going to be? Well, we know that there's 26 lowercase letters, right? So worst case, it would be lowercase 26. And that's pretty efficient, right? So when we check, hey, there's a lowercase a, but there's no lowercase b. So for this starts with function, we can return false. And that was done very efficiently, right? 26 is basically big O of 1. So this is a super efficient way to check prefixes, right? And that's why they call this a prefix tree. Prefixes can be checked very efficiently. So now let's actually jump into the code. All 3 of the functions, insert, search, and starts with, are pretty similar functions. So even though we're going to write a lot of code, it's going to be mostly similar. So let's...
For sure. Okay. I'm writing it in a while loop for this one, but I'm gonna try and do this right now. You know, we're gonna say node is equal to node child of the index for sure. We have if node child of the index is equal to none, then you return false. You want to return true at the end of it somehow. Actually, at the end of it, you might have to return false as well, because if node child idx dot word end is equal to none, is equal to true if idx, no, not idx, I is equal to len of word minus 1 and this node is true, then you want to return true. Okay, and then this starts with, you're going to have node self root I is equal to 0 while I is less than len of word, I is plus equal to 1. You return false by default, I think. Now it's not word anymore, it's prefix. So prefix, so let a prefix if so I guess I'll just have this idx equals, again, this ord of word, so prefix I is minus ord of A if node child idx is equal to none again, then you have to return false. If I is equal to len of word minus 1 and you return true, node equals node child idx, and then you return false. I mean, yeah, that's pretty similar. Yikes. Data class is not defined. We can't use data classes. That's alright. A trie node can probably just be created outside. Now word is not defined for sure because I think I did it down here. Null, null, false, false, true, null, false. Ooh. Alright, so that means, so null, null, false. So you inserted apple. Prefix, insert apple. Done. Search apple should return true. So there's a problem with the search. Search apple, search app should be false. Starts with app. Should be true, which it is. Insert app is null. And search app is true, but search isn't returning that. There could be something wrong with this. New node word end we're saying is true. It's pretty close. We're pretty close to making it right, but something's wrong. It has to be the word end, I think. So the word end might not be true, I'm guessing. So I'm just gonna say, you know, print node child idx word end, just to see. Yo, it doesn't even reach that. It doesn't even reach that. So it's gonna do this outside. It's gonna be false the whole time. Now what if we had print of I and len of word minus 1. Now that would be pretty obvious. Sassy, hello, hello. It's good to talk. Good to have you here. Word end isn't ever true. So when I'm creating this, am I ever reaching move to the next node? I'm going to say this word end could probably be done here. Oh, shoot, that's why. I think I know why. Okay, undo. I know why, but I also want to move it out later. Redo. It's because of this. Yeah, so now we have trues now, but it's still not getting the right answer, is it? So now the problem is with our final point here where we search app and we insert app. Yeah. Well, I think I know why. So this is why we need this outside of this if statement. So it's going to be the last point regardless. At any point, we're going to write this as node, paste this down here, which means we bring this like this. We can get rid of that so we can create this to trie node. And that should be fine. No! Bugs, man. Bugs. So insert empty, search empty, starts with A. You insert empty. Search empty. I guess you gotta just do the base case. Oh, dude. I'm gonna do the base case with this. Like the base case would be if word is equal to the empty string, then you would return self root dot word end. And so that would return true, but then starts with A should return false because this always returns true. Because I is going to be 0. 0 is equal to Yeah, one less, but we probably don't need this. Azula, hello. Welcome. Doesn't seem right. What is the type of your keyboard? It's an Ergo keyboard. It's called Glove 80. I put a link in it in the description. God damn it! This is a fucking bug. It's taking forever.
Hey everyone, welcome back.
Let's go to the solution here.
Try node, and all we're gonna do is just create the constructor. So in Python, that's what I'm doing, and net is basically the constructor. And I'm just gonna have a couple of member variables for this. So we are gonna have children of.
Okay, hold on. Let me just read this. So, how close is it to the implementation? Node while I is less than this, I plus plus, I is equal to. So this is index is equal to this, which current child index is equal to none, return false. Node next, so the next node is going to be this, which is fine, and then I plus plus. Return true. So this should be fine to start with. Now the search, this is where it gets fucked, I guess. That should also be fine up until oh, am I sure? Yeah, I just don't need that part. Here. Yeah, we'll have to try and see. Uh-oh. Time limit exceeded. Oh wait. It's not time limit exceeded. Alright, and insert. Current self root. Node equals this next one. This is still equals that. This is equal to the prefix tree node. Yo! Why is this correct also? How is this wrong in any way? How have I done this wrong in any way? I mean, this is a class. I did define this as a class. I wonder if that is the case. It was. I did it as a class attribute, as opposed to a node. Yeah. Okay. Alright, so that does simplify it when you don't have the if statement within the while loop. Fair enough, and look man, fair enough, right? Looking at that solution.
Hey everyone, welcome
Let's just
back.
read, watch this.
Constructor, so in Python, that's what I'm doing, and net is basically the constructor. And I'm just gonna have a couple of member variables for this. So we are gonna have children of a trie node, right? It could have children. It could have 26 children, but instead of doing an array, I'm just gonna do a hash map because that's easier. And remember, we can also mark every single node as if it was the end of a word. I'm gonna say end of word is gonna be a variable. Initially, it's gonna be false, but
Implement tree. 208 implement trie. Prefix trie. Or tree. Dot pi. Paste. Right quit all. Git add. Git commit. Solved problem once learnt. Try data structure. Git push. Exit. Okay, and we can probably copy and paste it here as well. Uh-oh. Oh, is this a problem? Just call it trie, I see. Instead of calling a prefix tree, they call it trie. Yo, is it that really that efficient? BS, man. That's only a one-time thing, isn't it? Let's see. Yo, it's consistently. Is it? Hey, it consistently beats other people using a while loop. Not bad, not bad. Only one of the only ones. Okay, try data structure. Pretty much I learned it now.
we could set it to true if the character was the end of a word. Notice how we're not actually storing the character itself in the trie node. That's going to be implicit from the hash map, from this hash map. So if we were adding a, let's say a character A, a lowercase character A, we would say to children, we would say children, for character A is the key, and we're going to create a new trie node for that character A, right? So that's how we're going to be doing it. That's how we're going to be inserting a node.
Sure.
So that's our entire trie node class. Now let's actually get into the trie class. So the first thing we're going to do is initialize this. So let's get rid of this comment. And for initializing this, all we're really going to need is a root node, and we can get the rest of the nodes from that root. So we're going to create a root trie node, and that's it. That's all we're going to do for the constructor. And once the trie node is created, we basically have an empty tree. Even though we have a root, it's empty because it does not have any children. So we technically have not inserted any words yet. But now let's implement the insert word method. For this method, we are going to have to iterate through every single character in the word. So we're going to initialize our self. Current is going to be set to the root. So we're going to initially start at the root, right? And then we're going to go character by character in the word. And for every single character, we're just going to check two things. does this character already exist? If it doesn't already exist, so if this character is not in the current nodes dot children hash map, right? So if this character is not in our hash map yet, that means it hasn't been inserted yet. So what are we going to do? We're going to create a trie node for this character. So cur dot children, and the key value we're going to use is the character, and then we're going to create a new trie node. So this is how we are going to be inserting characters. To children, we're going to use the character as a key value, and then we're going to create a empty trie node. And we're only doing that if the character doesn't already exist. If it does already exist, then we can skip that step and just say that current is going to be set to that child, right? So if that character already existed, then we can just update cur and move to that character and then continue our for loop, right? So we're going to do this for every character in the word. And then by the end of this loop, whether we have to create every node or the nodes already exist for us for this word, right? Let's say it was apple or something, the characters already exist, or we just created them. Now current is set to the last character of the word. So what are we going to cur and word and or no words for you? So this data structure can be pretty useful. It's a rare data structure to see on Leetcode problems, but I hope that you did learn something new today. And if this was helpful, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks.
Epic. Let me check something. Okay, cool. We're happy. We're happy. Let's a little bit. Okay. Alright, so we can close this for now. We got that live now. Alright. Not bad. Thanks for the few people who are, by the way, notifiers. Alright. Pretty good. Okay. What shall I need? What shall I want? Okay. This is finish watching this lecture. So CS restore to capture.
Some of you who have done the project now, there is a trie DLS and other people have actually options for ensuring forward secrecy is done. I think that's the kind of two things we do. So let us now look at the for the Diffie-Hellman things about recap from week 7. We have here, this is the textbook version of in the figure. So this is getting two users using only public key encryption algorithm arriving at a common secret. This protocol is clear? This everybody know about it. So Alice here now generates a private public key pair. So I call it PUA and PRA, and transmits the message to B consisting of PUA. So Alice tells that that is my public ID, and it also says the identity. Then B generates a secret key. Now in this case, the unique.
So RSA key distribution, A generates a public-private key pair and transmits a message to B consisting of public key of A and an identifier of Alice with an IDA. B generates a secret key KS and transmits it to Alice encrypted with Alice's public key. B generates a secret key and transmits it to A encrypted with A's public key. A computes the decryption of PRA of the encryption of PUA to get the secret key, and because only A decrypted the message, only A and B will know the identity of KS. Yep, A discards PUA and PRA, and B discards PUA. Okay, yep, this makes sense. This makes sense.
Initiator gives the public key, the receiver chooses a secret key, that is session key, KS, and transmit it to A by encrypting with public key. Okay. Now A, of course, he is the one who given the public key, so he decrypts it. And at the end of this protocol, both A discards PUA and PRA, and B discards PUA, but they achieved a secret with that. Right? So this is a straightforward, this particular algorithm. Interestingly, see, when the Diffie-Hellman, even before Diffie-Hellman thought about the Diffie-Hellman key exchange, people had this idea. So you can, if there is a public key encryption algorithm, you can always get obtain a common key exchange like this. This was there. Okay. So, whereas on the other hand, for the Diffie-Hellman, you already know. So I don't need to go through the Diffie-Hellman protocol again, right? So I think from the, let us say, so just to change the, the same thing I've done many times. One of the things that after studying this subject, you should be able to describe the Diffie-Hellman protocol from, from scratch. You should be able to write what are the general assumed general information about the algorithms, like a generator, the group structure, everything is known. So you set that as a generated thing. Then users using some random number, one user, Alice, generates G to the power of A and sends it to the other user. Other user chooses his own random number G power R B and sends it here. And both of them, since they know their respective secrets, they can actually compute the CDH output of the two random information that they have sent in the thing. And that is a common secret only known to them. And for others, it's actually, it will be one of the challenge questions for computation Diffie-Hellman, which is hard, so hence others cannot know. So some of these kind of information, you should be able to write down the things without much thing. Like you should be able to do this. In exam conditions, you should be able to do that, where there's like, G generator and things should be, so there should be a clear statement saying that they are the common feature of the group, and how the group structure is there, and the randomness chosen by the one user, randomness chosen by the other user, common secret chosen at the end of that. and then maybe it may have a man-in-the-middle attack and other things you should be able to describe. These are the things you should be able to describe in the exam condition. Okay, so is that clear? So I think you can expect one question easily of this kind of this flavor. Okay, whether it is in the Diffie-Hellman style or RSA style, you will have one of them. So once you have done that, so you got a common secret. So that is a master secret. So now you can see from there. Key derivation, a client encrypt key, the client MAC key, server encrypt key, server MAC key can be derived in this kind of format. Okay, this is how you, then after that, whatever the communication things are there will be encrypted using these respective master keys. Okay, more information about that is available in the book, but I think what is important is knowing these steps. So in some sense, keys now make up a connection state. So connection state is defined by the following parameters, like a server and a client random, and server and a MAC secret, client and write MAC secret, server write key, and client write key. So these are all make up a kind of things. So there is some initial vectors and sequence numbers to maintain the state of different TLS protocol things. This is a general connection made up, and the full TLS handshake it goes as follows. So it has totally 4 different phases. You can see that initially client says client hello and server says server hello. Then after that, server sends the certificates. Okay, it doesn't care in this case. It doesn't care about the certificate of client. Server sends then the certificate, then the server key exchange, certificate request, server hello done, and if required, so first the client sends a certificate if required, requested. Client sends key exchange and client may send client verify thing. And after that, we have a chain cipher spec, so which means that they will negotiate what kind of a ciphers they use at the end of this and finished, and finally chain cipher and finish. At the end of this, both client and server now have all respective functions to start communications. So, and for that you need a different record encryption. So the application data is there. Got a different fragments, and sometimes you may even compress, and you can also add MAC, then you have encrypt, and then finally that will become a part of the SSL record header, and that SSL at the SSL layer these records are exchanged. So then a session resumption is, for example, a new TLS handshake is required per TCP connection. Loading a web page can require, for example, for 100. To save time, what you do is you reuse master secret. So the whole, the suite protocol suite you have, that complication comes because of all this reusing master secret and in all those details. So session IDs are there. Client, server, and each store a master secret, and ID is opaque to handle, so can be a hash of some master secret. Session tickets are only clients can store tickets. Ticket is encrypted by master secret using long-term ticket key on the server. So there are a lot of security issues with this. TLS is a very complicated software. Many corner case protocol bugs were there. kind of some other like breach, crime, poodle, drown, and lick jam. So many things are there, and many subtle implementation bugs are there. And there is one with recently that the heartbleed become very famous, where with that with a client and server, it would you kind of force the server to send some information in its memory, even though everything is finished. So slowly the client is able to draw meaningful information from that, and it's actually the attack is become quite dramatic, and that was initiated in the Heartbleed. So very slow to upgrade to servers now. TLS 1.1 is still running 15 years or later. So what are the improvements? TLS 1.3 is you have reduced complexity, and that has only Diffie-Hellman style thing and only 5 cipher series, and you get the forward secrecy because of that. Then there is also reduced latency. Then verifiability is that the protocol is verified by automatic tools. So I think instead of me going through all of that, I think it will probably easier for you to kind of go. And some of these websites give you like all details of the TLS software. So if you go through, for example, here, so I checked. So you can see, okay. So this one, you can go here, the illustrated TLS 1.2 connection. Every byte is explained. So all the protocol connection is explained here. So if you are want to, you can actually browse this, you can get a lot of practical knowledge with this, right? So I'm not going to in detail all of this in this one, yeah. So okay, so in some sense, so this is all about a very short lecture on SSL. I have kept some additional material in the same module about TLS layer from the textbook that has a bit more information. But I think from the practical, from the cryptography side, for the examination point of view, you need to be able to kind of state this hybrid protocol using or maybe using certificates. Certificates we discussed in the other lecture. Certificate has basically certificate has structure, PU, the public address, and a signature from the KDC. So KDC has a PR authority. PU authority is the public key of authority. Then you should be able to explain the certificate as from those point of view. I think which I have explained. Yeah.
I have a question about certificates. Is the reason SSL certificates are free, is that because they shouldn't be used?
SSL certificates are free.
Certificates, you can get them for free, but TLS ones you have to pay for. Is the reason they're free, the SSL one, is that because they shouldn't be used?
That's not probably the main reason, but as I told you, the TLS the changeover trajectory is because of security and other issues, but the certificates paying and other things is actually interplay that might have happened because of the whole industry that was created to give the security, right? All these the big companies came up, and probably now all the security companies have been swallowed by some big players like Google and others, So whereas they are probably adopting methods to suit their business model. So I don't know how to answer that question, but yeah, but the main reason is main thing is because it's all about the change of methodology of the maintaining the new versions. So this has changed, and what I have seen in last few years because of working with this post-quantum cryptography I've seen, now all the softwares need to be post-quantum secure. But we don't have post-quantum secure algorithm yet, or it may change over the time. So one thing is certain, that change is the, especially with respect to encryption, anytime you may need to change over. So all the cybersecurity softwares and all following what's called agile programming kind of methodology, where they should be able to quickly change the software whenever they want. Or even let's say, when do you get a new version? How do you deliver a new version to your thing? So there are a lot of innovations are happening, and obviously when there is an innovation, means there is this industry, and so all that. If you go to some practical side, there'll be a number of cybersecurity companies, so many of them now. It's a very big. I don't have any view right now on that. This is a ever-changing area, but because of the post-quantum cryptography, so for example, there are new standards coming up with NIST has put up, and some of them actually do much better than RSA, except that you have a lot much of bytes to exchange in the TLS connection, but they are sometimes more efficient, faster as well. So this is happening. This is so slowly we might change over to post-quantum cryptography. So is that kind of a situation? Yeah. So this is, this one application is any cryptography, applied cryptography subject should have TLS, or let us say this one, because this is the main bread and butter of public key cryptography. So even though you can think RSA started with RSA Incorporated, that company in 1984 itself, around even early in that decade, but they didn't sell any software until then. We have Netscape. Then after that moment, this idea came. Look, this particular one. You can see here. The server doesn't care who you are. It says, this is my certificate. Okay. So whether a server has a client has a certificate or not, server has certificate. So with the result, what happens is that whatever may be the different devices connecting to the server, anybody can actually talk to the server without like a secure pipe. You can establish a secure pipe, and this was the main contribution of public key cryptography. This was unimagined. This was not possible with the previous encryption technology. So that's why, and then of course, there are other specialized software worker where you also need a client certificate, whether the client certificate is valid or not. That's included, but just before, you can see that even the evolution of this kind of thing has that imprint, because you don't need, you say if you are building and giving service to web service, for example, secure web service, you have to, you can actually enforce security by preparing a good server. You don't care about whether the client in different things, the software is well structured or not, but if you have a good software, so that will give you the security. So this is a philosophically, or even kind of it changed. It's like a public key cryptography became the center of security at that time. Yeah. So till around 90s to 92, when time, RSA, people are using RSA for 700, 800 bits, and nobody was serious. Okay, public key is there, but you can see that all communication products at that time, around 80s and all, they were done with symmetric key encryption. And let's say if you have a walkie-talkie, you come to the every day in the morning, you initialize the keys in the morning. So there is a key for the day, key for the week, key for the month, like that, and then you go and start using. So all the police, paramilitary people they were using, already encryption were used. But so that kind of a thing came back only when the mobile phones became quite popular later. So that there is a difference of almost 15 years before symmetry. All the products which are symmetry key got transferred into hybrid kind of encryption. So now, for example, this mobile phone, it actually has power of big PC when it was in 1980s, 90s, because even though it's a small machine, it has all that power. So that's why I think mobile companies, they continue to grow. Yeah. So this is the kind of thing, one application. So maybe I would have continued with another application of advanced application of encryption with using some other esoteric data structures like trees and etc. But probably we don't have time that much. So I think from the exam is now scheduled on the first week of examination period, and you are still working on assignment 2. So hopefully everybody would be, I think, so don't try to postpone it. For some reason you're asking for extension and all, will only make your, it's not going to help you. Like it's better to finish off assignment 2 quickly and start preparing for the exam. So that's why next on next Tuesday, so if the guest lecturer, I think, looks like he's quite busy, so if he doesn't come or not, but I'm going to use it for example, for exam preparation. So I will give another test quiz, which has which has multiple choice questions, That means and it's also like a random. That means when you get it, the questions will be chosen. Say maybe for question 1, it's out of 5 questions. Question 2 is out of 10. Question 3 out of 50 questions. So you will, each time when you answer it, there are lots of questions, and that require you to practice all the other additional things that we learned throughout the subject. So you can probably do as many as you can before the exam. So that will help you to, all those formats, theorem questions, and all you may answer. Yeah, that I'll do, and then also kind of starts a revision. So with the view of like how much you should spend for the exam things, etc. And we'll try to give your assignment to you back as soon as possible. But the next week is where you send your reports. So the reports may not get marked before the exam. But anyway, you don't have to. You would have probably done with it, and so the exam is on the material that is covered in the subject. So. So we will focus on the exam thing next week. So if you come in large numbers and ask questions during the thing, that might help your thing. So you can tell your friends, it's probably recorded. You may do it, but if you are come on there itself instantly, you can satisfy your questions and all. Okay, that's what I'm going to do for next week. Mostly that, yeah. Yeah, and for the research project, I think we have given the feedback at the end of the thing. I think I'm happy with the work done by most people. There are some very interesting projects as well. But I think to get the mark, you need to show analysis and the technical coverage. That's very important, and that should be. There is not.
Okay. You just told me about random stuff now. Cool.
Yeah.
This material is made available to you by or on behalf of the University of Melbourne under Section 113P. This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968.
In Australia, and I said, oh, if you attend, this will also help you in your examination, for the exam. Any help here? Absolutely not a cryptographer. I did undergraduate maths. How do I? 40 years ago, and some postgraduate statistics. It's better. I'm at the maximum here. How do I? Pardon? It's not connected to the speaker, right? Exactly. A lot to do. How to do that now? Last three. A bit of a doubt. How should I do that? So it's running on my computer. Maybe if I do it from here, does it help? Skip. And he has contributed to Australian payments network. Most of the things. So today he will be talking to us about the basically. I promised you to have a guest lecture, but I think the other speaker from the same organization, he didn't come back to me yet. This is about Australian payments network. Have you all, anybody familiar with Australian payments network? No. So it's a kind of a non-profit organization helping Australian businesses and others to have standards and others in place for payments. And one of the things, the things that we have learned in the subject is, DES and triple DES. In the financial
Bro, what's the percentage on this? We'll check. Yep, I'm gonna have to charge this. Okay. Love how I can't hear half of what's being said.
to migrate it to AES. The AES is considered to be very strong compared to triple DES. Triple DES was introduced mainly to address the security issues that emerged during the time when DES was there. So for financial industry, they use triple DES that have enabled them to actually have an equivalent of 112-bit security, which you have studied in this subject, right? So, but there has been a constant move to increase the change it over to the change over to the AES one. And so this is called AES migration. Migration to AES is a big project in Australian Payments Network. And there are lots of issues in this. Yeah, it's not easy to move to a new standard so quickly. And I think by 2025 or something is a deadline that everybody in every financial institutions need to use AES. So some of the security issues that come out of that was Paul gave a talk last year. Perhaps we could just watch that. Yeah. And you're also finalizing your research report. These are relevant for you to also know. Yeah. I'm sure if you attend, this will also help you in your examination.
Let me see if I can hear that.
It will help you in thinking about the applications of cryptography. Yeah.
Undergraduate 40 years ago and some postgraduate statistics, and my master's thesis was entitled Radio-Labeled Antigenic Suicide. We had an annual tin automobile issue as had fires. So this, although it's an old paper, silly
I'm working with some equations. 10, no 17, and I think still is on. You have any comments, any questions? Pin. And they are available on LMS, so you can go through and study yourself. This part, okay. So let's go to LMS. So this is the, so if you go to quizzes, for example, I have practice short answer questions in cryptography and security. There is a new quiz. This is as I promised you last time, this has lots of questions. For example, here, preview. We got questions like this, and you can go and answer. Questions up to there is about 10 questions. 10, no 70 questions, but they are actually picked randomly from a question bank. So when you do it, you will have many questions. So to work with, So this should help you to answer the questions in the exam. So please make use of this. Okay. So, but we'll also release practice exam tomorrow, hopefully by tomorrow, and I will also give some hints to do that, and so that should give you an idea of how the exam should be. There will be 8 questions, and first question is some multiple choice, and there's some short answer questions. Then depending on different topics, you have questions. You don't have to. I think there was one question on the. One question on was do we want to remember all the things? It's not about remembering. It's about probably understanding. So the questions will test about your understanding of the matter. So in some cases, the protocols, there may be some steps that you need to know, but there is nothing like rote memory. There is no need to rote memorize things, but so for example, in a signature algorithm or an LKML algorithm, you need to know the steps.
You should know the fundamentals, right?
For example, if you are encrypting a message M by using public address, public key, so what is the nature of the public key there, how the encryption happens, so all the steps you need to know. So if you understand fundamentally the process, it would come naturally. There's no, so I won't be asking any question just to recall memory, but when you study, probably some amount of memory is needed. Otherwise, where is the exam? Yeah. So there's no need for rote memory, but required to have a memory with understanding. Okay.
Yep.
Those are the 2 things. And so you can do some of these things and let us know any kind of thing. And tomorrow I will go through the review one by one and point out any like how to study. For example, in this case, hash functions. You need to know the requirements, and you should be able to reproduce the requirements in the exam conditions. So that doesn't, for example, if you just learn this rote memory, and if you don't know how to utilize, how to apply pre-image resistance or second pre-image resistance or strong collision resistance,
you should remember that.
That's of no use, right? So if you understand the differences between these 2, and then for example, practice like that, automatically you should be able to work during the exam. It's 2 hours exam, so I can't ask you to reproduce the things that we entirely taught in the whole thing. So I think those are the things that that requires.
It's going to
I'll
be
go
kind of
through the
tough.
review tomorrow, not today. But I think other day, one student asked, actually, he wants to know whether he's there now or not. Elgamal, so for example, Schnorr signature. Is there? I think he may not be there. Maybe if he comes tomorrow, I may go through again. But I think I can probably go through that. So maybe even before understanding that, what key ideas of Elgamal signatures need to be understood. Here and some of the background, like if you are coming up with a Elgamal signature, what's the main idea behind it? I think if you understand that, then you can solve any problem with respect to a thing. So you have already solved one problem in the assignment, where the verification equations and the signing equations are not secure, because there is some insecurity there, and you're able to understand, oh, why? Or if I can use in that way, then it won't be working. So whereas here in the Schnorr scheme, the equations, like the verification and the signing equations, require you to do a minimum number of work, and that's the beauty of Schnorr signature. It just came 2 years after Elgamal, but he also had a patent, and hence until 2008 they were not using it. But now Schnorr is there's no restrictions now. It's being used for blockchains and so forth. Okay, so you want me to go through now this one? Yeah, this idea, or you can do it yourself, or you want me to? Okay, I'll explain to you. See, look here, Elgamal. So in case of Elgamal signature, what you need to understand, two basic features. So the scheme is kind of supported by hard problems, which is a discrete logarithm problem. So you can look at the public key. G to YA is G to the power of XA. X is the secret, and so given G power XA, no one can get X, because that's the support. Now that's the only thing. But then main idea why we are able to link a particular message and a signing equation. So you are trying to link the message to be signed with some information that you owe, which is a private key. Okay, so you can see there is XA, which is secret, which is known only to the signer. Okay, nobody gets that. From G power XA you cannot do, right? But if some equation involved with XA, okay,
Camel signature scheme. Okay.
see, there is XA, which is secret, which is known only to the signer. Okay, nobody gets that. From G power XA.
Was that in week 12?
you cannot do, right? But if some equation involved with XA supported by hard problems, which is a discrete logarithm problem. So you can look at the public key. G to the YA is G to the power of XA. X is the secret, and so given G power XA, no one can get X, because that's the support. Now, that's the only thing. But then, main idea why we are able to link a particular message and a signing equation. So you are trying to link the message to be signed with some information that UO, which is a private key. Okay.
Okay. Math extensions, MST solutions. CS major. Yes, I am a CS major. I already graduated, but I'm doing my master's.
Dear guys, welcome to watch the preparation video for the problem set 11 game theory. So this will be the last preparation video for the last tutorial. And inside the game theory, basically it's pretty easy because we didn't touch like the very deep concept. And for the basic concept we have is the game itself. In order to answer the question, we need to understand about the game itself. And we have two different type of games. We have the normal form game and also the extensive form game. Inside the normal form game, how we can formally define a game? We have all those elements. So basically, it's the n, the set n represents each of the player. We have player 1, player 2, all the way to player n. And in the normal form game, we will have normally we will have 2 players, but we could extend it to have more than 2 players. And then the AI represents the action, the strategy each player can choose. So we have an index of I, so representing each of the player. And for the action or the strategy the player can choose, basically we have 2 different types. We have the pure strategy or mixed strategy. Pure strategy basically means the player will choosing only one single strategy, only one single action. And the mixed strategy means the player can choose different action with the probability distribution. And for example, like this, 50-50. The summation of the each actions will equal to 1 for each of the player. And then we also have uppercase A, this A over here. We represent this, basically this means a profile. So what does the profile mean? It's kind of like a state in the classical planning domain. Basically, it's a combination of each action from different agents. Like A for agent A1 times A2 all the way to AN. So basically for each of these action is a action chosen by the player. So we call those as a profile. So basically the uppercase A represents a set of all profiles and the lowercase a represent one single profile, like one single state. And the last thing we have is a utility function for different agents. We call it UI. So basically for different agent, we have different utility function. And the utility function will take a profile as input, and we will return you the utility that agent I can get from this profile. So this is a utility, and which is the basic value we try to maximize inside the game. And besides those 4 elements, we also have a few assumptions we had in the normal form. And the most important assumption we have is each player will choosing the action at the same time. So they don't have any like additional information. They don't talk to each other. Each player will choose action at the same time or choose their strategy. Let's use strategy at same time. And then we have the second one, which is the extensive form game, and the main difference between those two is the assumption. So for the extensive form game, it doesn't have the assumption that each player will choose the strategy at same time. So we can assuming that one player will choose first and the other player will choose later. Like this one player mainly means yourself, so you will choose the action first and the other player will choose the action later. So that's the extensive form game represent. And then for the game theory, we also have a few different approach algorithms to solve it. And basically we have those concepts. We have a dominant strategy. Basically in the workshop you will learn like the strong dominant, strictly dominant strategy, or the weak dominant strategy. So basically it means we have a strategy which the utility value of that strategy is always larger than the utility of any other strategy. So that's the strictly dominant strategy. And for the weakly dominant strategy, it will be larger or equal to, like this. And we also have the Nash equilibrium, which is another concept. Basically saying that if we take 2 players as an example, if we are saying that player 1 and player B choosing two actions, the action A and action B, if none of them can change their strategy to improve their utility, we note this state as a Nash equilibrium state, which means they achieve a balance between those two. And we also have the concept of the mixed strategy. Basically, the mixed strategy is kind of like a Nash equilibrium with the mixed strategy. So in a lot of problems, we don't have a Nash equilibrium state, but we can achieve the Nash equilibrium using the mixed strategy. So basically, you will learn all the. We will have a workshop question around all those three concepts in this workshop, and we also have some other approach. For example, like the backward induction or the minimax. They are belong to the extensive form game. They are not covered in this workshop, but they are still very important concept. You should understand that. And one last thing is in the game theory, we often talk with a lot of examples. So, for example, we have the prisoner's dilemma game, which basically we have two prisoners, and each of them can choose to cooperate with the judge or don't cooperate with the judge. And we also have the golden ball example, which also from the lecture, and we also have the auctions. Auctions is a very interesting example which are used in the game theory a lot. So basically, it's a rational game, and in this workshop, we are going to introduce different ways of auctions, and try to think when we introduce the auctions, try to think about what is your dominant strategy, what is your best choice for each of those auctions. And I think that's all we should know for this workshop, and good luck with this workshop, and also good luck with the exam. Hopefully not see you guys next semester.
Alright, I'm gonna go eat, go to the gym, be back in around 2 hours. Alright, 2 hours total, roughly. And yep, we'll be good. So, catch you guys in a bit. I'll put on some lo-fi music. I'm back. Except, I got my parcel for a dual monitor arm, and I might need to set that up now, as well as have a shower. So I'm back from the gym, but I'd have to have a shower and be back after that. So yeah, there's a little bit of a miscellaneous task that we're going to be doing. So I'll still keep the lo-fi music going for a bit. So BRB once again. Okay, I'm back, but we gotta try and set up. Ooh, maybe I gotta charge a little bit. I gotta set up a new monitor arm. Okay, so try and stream this a little bit. The question is how? How am I gonna do it? Trying to see, like, if I turn off the background. Okay, so you can just see my screen. I don't want to do it like here. Maybe that. Worried that it'd fall. Is it really? I need to face it downwards. Doing most. I mean, I could do it like this. Horizontal. Is that good? Yeah, that's alright. We'll turn off the display volume. Now just worry about this. Let's turn off the music. And I don't know, we'll keep it like this for now for a bit. Down a little bit. Fall. Okay, I don't think that would fall. I think that's alright. Okay. How do you sync Obsidian between devices? That's a good question. I use Obsidian self-hosted live sync. That's what it's called. So that's what I use. Now I have scissors. You can't see that, can you? Yeah, you can. Didn't need to get an extra box. Really funny. Is anything blocking? No. I mean, the chair's a little bit. It's alright. Oh, you started using Git today for syncing. Yeah, I use both. I use Git and yeah, I use Git as well for it. The thing is, I gotta see. Let's have a look. Maybe I'll put it to full screen. Should I? So what's the best option? I use both. That's the thing. Like I commit to Git and I use self-hosted LiveSync. The problem is you use both because you need one for syncing between devices, but another one to ensure you have version control, right? So they're different use cases. At least those are my use cases. Yeah, so the heat map thing, heat map on your GitHub, that's true. Now, I don't use GitHub for my Obsidian notes. So I use Gitty, which is a self-hosted version as well. So everything on my Obsidian is self-hosted and nothing is actually stored on the web. So that's a plus. That's a plus for me, at least, I feel. So none of my data is actually on the web that I'm actually typing into Obsidian. This is like Christmas and unwrapping new stuff. Except I don't know how to take this out. That dropped right on my foot. Wonderful. Gotta make sure you put everything in an orderly manner. And then we can move this to the side. This is one. This is two. This is one. The base is crazy. And this is another one. And we got cleaning and maintenance guides. Nice, so this is like on the last page for sure. Interesting. Oh, this last page is for like Alright, we'll see. We just have a look. Have a suss. Could you write the name of the Obsidian extension? Yes, I can. Give me a sec. It is self-hosted LiveSync. Self-hosted LiveSync. That should be what you need. Okay, I tucked my hair behind my head. Now, the problem is how I'm do all this. What do we have here? We have zip ties, turner. Is this the base? I can see how this works. This makes sense. We're gonna have 4 of those. We're gonna have to put one of these. Ideally, I would like this to just stay alive. Can I move this away now? Oof. Move my iPad away as well. Okay. Man, it's localized. It's me right there. What am I gonna... What do I need to do here? Damn. We actually got to like move this a little bit. This is gonna be kind of scary, if otherwise. So I'm gonna try something. It might be bad. The screen is still just... Alright, we're literally gonna have to pause the stream for a bit and then we'll be back, but in the meantime we'll just play some music.
找不到这个动态才行。现在我干脆要等。小弟啊，自己挣钱自己花，嘿嘿。哎呦，这回可以摆4个computer 在转来转去了。呜呼，我的小大灵哎。好，自己创造财富啊。要问妈妈要，妈妈也没那么多钱给我，对吧？自己挣钱自己花。
对。
这样的话你也买。
对。
妈给你买
Yeah.
饭吃都是很重要。
Alright, epic. Like we got everything set up again. It's unfortunate that it takes quite a bit of time. Okay. Now, I wish I could take a screenshot of the progress that I made. Do it now. Do it like this. Dual monitor. And I will share it to the MacBook. This is what it looks like. I turned on FOV. Okay, you can see my cameras on my iPhone. But we got dual cam now. I mean dual monitor. Yeah, these two top bits here, like if you zoom in on these bits right here, these two bits, there's like actual caps for these, but they don't seem to pop in. But there it is. It's done. And we shall wave to the new people. I don't know, why does this pop up twice? That's interesting. I don't know why that has to pop up twice. Happened only recently. Yeah, I don't know. I didn't do anything. Okay, so now we can, I'll clean up the rest of what I have on the side later and what I have on the floor. However, looking at my surroundings, I think there isn't much else that needs setting up. I can push this back. Oof. Ooh, this is a good setup. It's like I got an iPad here with the monitor. Yeah, okay. Not really necessary to have this many. But it's a thought. It's a thought. But now I can push back the monitor further back on the monitor arm and then have my iPad with some more free space here. So pretty cool, pretty cool. And I could do an extra screen. Okay, so that's mirroring, but I want to extend the display. Hello, ShubiHH. Mirror or extend will mirror. Take some, okay, you can't access it for some reason. Doesn't matter. Close it. Okay. I can take this off. I can take this off. Okay. Cool. Now we can try and do some more study. We're gonna do El-Gamal just because I feel like that's one of the more salient things that I need to remember. at the moment. Alright, let's see. I gotta restart my Firefox. Okay, let me stand. Ooh. You guys heard that? Yo. Okay, there's nothing bad that happened. It's just, it's too high. I should have realized actually that this would happen. I should have tested it. But okay. Maintenance. I'm gonna maintain something real quick. We need a longer wire, that's what. I know how to have a longer wire. Okay, give me a second.
That is, we could either select randomly, which isn't going to work very well, but it's very... In this section, we'll look at extensive form games. Extensive form games are sequential games in which agents play actions one after each other, which is different to normal form games where actions are played simultaneously. We'll look at how to calculate strategies and the Nash equilibria for extensive form games using a technique known as backward induction, and we'll also look at how to solve these games using multi-agent reinforcement learning. After this section, you're expected to be able to identify situations in which extensive form games are a suitable model of a problem, define the strategies and Nash equilibria for an extensive form game, manually apply backward induction to small extensive form games, design and implement backward induction to solve medium-scale extensive form games automatically, and design and implement multi-agent reinforcement learning algorithms to solve extensive form games automatically. Let's get started. Let's look at the following game, which is a normal form game called the buyer and seller game. In the buyer and seller game, there's two players, a seller who's trying to sell a product, a buyer who's trying to buy a product. The seller can manufacture either a high quality product or a low quality product, and the buyer can choose to buy the product or not buy it. If we solve this using our theory from normal form games, we can see that the seller has a dominant strategy to sell low quality products because they will get a payoff of 3 instead of 2 if the buyer buys it, because it will cost them less to manufacture, and they'll get a payoff of 1 versus 0 if they don't sell it, because it will still cost them less to manufacture. The buyer doesn't have a dominant strategy. They would prefer to buy a high quality product at the same price than a low quality product. However, because we know the seller's dominant strategy is to sell, we can eliminate the row for the buyer and determine that what will happen is that the seller produces a low quality product that the buyer never buys. And this is the Nash equilibrium for our game. So the incentive then becomes for sellers to manufacture low quality products and for buyers not to buy them. And this isn't a great situation for anybody, because a much better outcome is this top left. Similar to the prisoner's dilemma, if each agent acts self-interestedly, then they end up with a worse outcome than if they acted globally optimally. But actually, this isn't what happens in real life. Even if this is a toy model of a problem, it's still a model of buying and selling products. Why is this the case? Well, it's because people can usually assess the quality of products before they buy them. So for example, what they can do is go into a shop and look at items. They could return items for a refund if they find it's lower quality than what they thought, or they could go and read reviews about that item. So effectively, sellers have to play their move before buyers, rather than simultaneously like we see in a normal form game. So in reality, the real game would look more like this. In the top right corner here, we have an extensive form game. In an extensive form game, the players take actions sequentially rather than simultaneously. If we look at this game, we can see here that at the top node, a seller has a move where they can choose between to either sell high quality products or low quality products, and then it becomes the buyer's turn who can choose to buy or not buy. This model of the game, sequential games, are called extensive form games, and they form what we're going to talk about in this part. Let's go through a definition of an extensive form game before we look at how to solve it. As we can see here in the top right, an extensive form game can be represented as a tree instead of a matrix as we did in normal form games. We're going to look at perfect information games. Just as in normal form games, perfect information simply means that all of the players in their game are aware of each other, the moves that each others have, the outcome of all of the moves, and the final payoffs of all of the paths through the tree. This is as opposed to imperfect information games where, for example, parts of the state of the game might be hidden. A perfect information extensive form game is a tuple, G, with the following elements. N, which specifies the number of players that are in the game. S, which is the state space of the game. The definition of a state space is the same as in a Markov decision process. The states are represented by nodes in our tree. S0, which is the initial state, which we circle here as the root node of the tree. A, which is the actions that are available to players. T, which is the transition function that determines what happens in a state, which state it comes to afterwards, same as we've seen earlier in MDPs. P, which is a function that determines which player has the move in the current state. And R, which is the rewards we get at the end of an episode. The main difference between an extensive form game and a Markov decision process is the fact that there are multiple agents in the game. We can see this in the definition of the tuple and the elements. First, we have a number of agents in the game, whereas the Markov decision process assumes there's only one agent in the game, or perhaps more accurately, there might be multiple agents, but there's one agent that has control over all of the actions. However, the action function is slightly different in that it tells us the actions that are available to each player in a state rather than just to one individual player. The transition function is the same as before. However, we have this additional function P. P is a function that takes a state and returns the number of the agent whose turn it is at that state. So this means that at each point only one agent can possibly take a turn. Finally, the reward function is also slightly different. As before, it takes a state, but instead of returning just a single real number, it returns a tuple of real numbers, one for each player. In some text you read, this may be called U instead of R, referring to utility, but in this we're going to use R to be consistent with the rest of the reinforcement learning literature. Typically in an extensive form game, we only receive a payoff in the final state of the game rather than as states throughout. However, we can model receiving rewards along the path as well by just simply summing them up and specifying the cumulative reward at the end. The model's the same. In an extensive form game, we have the same assumptions as for a normal form game. All of the agents are rational and therefore able to calculate the best strategies for each other. They're all self-interested and they don't care about the payoffs of each other. The game is perfect information, meaning the payoffs are known. The transition function is common knowledge between all the agents. The only difference is we don't have simultaneous moves in this game. So how do we solve perfect information extensive form games? We can solve it using a technique called backwards induction. I'm going to illustrate how backward induction works and illustrate some of the key concepts in extensive form games using the buyer-seller game in extensive form. So in this case here we can see that we have a game where each player gets exactly one move, but the seller gets to go first. We solve this using backward induction by starting at the bottom of the game in order to solve it. And what we solve is each sub-game of our game. At the bottom of the tree, the sub-game is the final moves that we have for each player and the payoffs that they will receive. First, all we do is solve each of these sub-games. So let's have a look at these two sub-games that we have at the bottom here, where the buyer has to make a choice and determine what we think the buyer would do. In this notation, the buyer has their payoff in the second element of the payoff tuple. On the left sub game, the buyer has to make a choice between buying and not buying. If they buy, they'll get a reward of 2. If they don't buy, they'll get a reward of 1. Clearly 2 is better than 1, so the buyer is going to select to do this. What we then do is we backpropagate the outcome of this game up to this node. Effectively, we know that if the buyer is rational and self-interested, the outcome of the game at this point will be 2-2. We can do the same for the other game, the other subgame. In this case, buyer number 2 should prefer to not buy because they'd rather get a reward of 1 instead of 0. So we'd say this, and again, we backpropagate the rewards up to this node here. Because at this particular point, if we assume the buyer is rational and self-interested, we know the outcome of the game is going to be 1-1. So now that we've solved those two subgames, what we can see is the next layer up is another subgame that determines which choices a seller should make. Because we've propagated up these values using our backward induction here, now we need to do is make a decision over which choice would a seller take between these two outcomes, 2-2 and 2-1. Clearly the seller is going to prefer to get a reward of 2 instead of a reward of 1, therefore they're going to choose to make a high quality product. Again, we backpropagate this value up to here, and what we see at this root node now is that the final outcome of the game will be 2-2 if both players are rational and self-interested. So you can see here the backward induction is the idea of solving each subgame at the bottom and recursively solving the subgame above it until we reach the root node. So a few bits of terminology that are important here. The first one is the terminology of subgame, which we've already covered. The second is the idea of the equilibrium path of this game. The equilibrium path is a path from a root node down to one of the final nodes that specifies the move that each player will make at each point, and this becomes our equilibrium. In this case here, this path is our equilibrium path. Assuming all the players are rational and self-interested, the seller will choose high, the buyer will choose buy, and that becomes our equilibrium path. A somewhat related concept is the concept known as subgame perfect equilibria. Which we abbreviate as just SPE. The subgame perfect equilibria of a game consists of all the strategy profiles for all of the agents, such that for any subgame of that game, the strategy for the player that's playing at that node is the best response for that player. So the subgame perfect equilibria is not just the equilibrium path on here, but also includes this strategy that we have here of the buyer not buying should they come into this state here. So in other words, what we have as the subgame perfect equilibria is the strategy that each player would play for each subgame. So therefore, backward induction is simply solving each subgame starting from the bottom and then using the outcome of that game to solve its parent game. At each point, we're just solving the game that's at one node. In a subgame perfect equilibria, it must be that the strategies that we have, these ones here, constitute a Nash equilibria in every subgame. An interesting note is that if we have a two-player zero-sum game, backward induction gives the same result as the well-known minimax algorithm. If you don't know what that is right now, don't worry about it. But what we're effectively saying is that backward induction is a generalization of the well-known minimax algorithm. Minimax won't work for more than two players or for non-zero-sum games, but backward induction does. But if the game is two-player, non-zero-sum game, then the solution will be the same as minimax. Now we're going to look at an example called the advertising game. You might remember Remember this as the advertising game. That we saw in the normal form game section. In that game, the equilibrium was such that firm 1 didn't advertise and firm 2 did. This gave us the outcome 713 for firm 1 and 2 respectively. But what if, for example, firm 1 had had a chance to advertise before firm 2? Would this change the outcome? Let's have a look at the game and what it would look like in extensive form. In this exercise, try to solve this extensive form game using backward induction and see if we get a different outcome than we did in the previous game. Okay, so do we get a different outcome? Let's have a look at how to solve this using backward induction. I'm going to start with this subgame here, and I'm firm 2. My payoff is in the right hand tuple. Do I not advertise or do I advertise? Not advertising gives me a payoff of 7 and advertising gives me a payoff of 6, so I'm not going to advertise. That's going to be my subgame perfect equilibria, and I'm going to back propagate the value 13 and 7 to this node. Now I'm going to solve the second subgame over here. Firm 2, do I not advertise or do I advertise? Well, advertising gives me a payoff of 13 instead of 12, so clearly I'm going to select that. That becomes my subgame perfect equilibria for that game, and the outcome is 713. Now I solve this subgame for firm 1 by using the back propagated values. Does firm 1 prefer to receive a payoff of 13 for advertising or 7 for not advertising? Clearly they're going to advertise and get a higher payoff. So this becomes our equilibria, and the outcome of the game is 13-7. So we can see here this changes the outcome of the game, which previously was that firm 1 didn't advertise and firm 2 did. So by firm 1 taking the first action, they actually gained an advantage. Note that going first isn't always an advantage of a game. Determining, for example, where to attack and telling your opponent before you attack is usually a disadvantage. So sometimes going first can be an advantage, but that's not always the case. Now it must be that the strategies that we have to firm 1 didn't advertise and firm 2 did. This gave us the outcome 713 for firm 1 and 2 respectively. But what if, for example, firm 1 had had a chance to pay off? So the entire game can be an advantage, but that's not always the case. In the next few parts, we'll look at multi-agent problems, otherwise known as games. By games, we don't mean digital games or board games like chess. Now let's do an exercise on a game called the advertising game. In the advertising game, we have two firms, firm 1 and firm 2, and they each have to decide whether they're going to advertise in order to generate new business for themselves, which will take business away from each other. They can either not advertise or they can advertise. The payoffs in this game aren't symmetric because the two firms are different sizes and therefore they get different advantages for choosing to advertise. If neither firm advertises, then firm 1 gets a payoff of 16. We could say this is, for example, $16,000 per month that they earn in revenue that month. Firm 2 would get a payoff of 12. On the other hand, if firm 2 decides not to advertise but firm 1 does, then firm 1 will take some business away from firm 2, but its payoff will go down because the amount of business it gets is not enough to cover the advertising costs. On the other hand, if firm 2 decides to advertise and firm 1 doesn't, then it takes business away from firm 2. But also it gains so much business that its overall profit increases because the amount of business it gains is more than the advertising cost. If they both choose to advertise, then their payoffs are 6 each. So the payoff goes down for each of them because the cost of the advertising is high, but they don't gain any new customers if they each advertise. Your job is to solve this game. Do the players have dominant strategies? If yes, what are they? If no, why not? Is there a Nash equilibrium in this game? Try solving this and see what your answer is. So how did you go? Did you solve the game? Well, let's have a look at the answer. For firm 1, there's clearly a dominant strategy. If firm 2 chooses not to advertise, then clearly firm 1 should not advertise because it gets a higher revenue, payoff of 16 instead of 13. Similarly, if firm 2 chooses to advertise, firm 1's payoff for not advertising is 7 versus 6. So this is a dominant strategy for firm 1. Does firm 2 have a dominant strategy? Well, we can see here that if firm 1 chooses not to advertise, firm 2 should advertise because it gets a slightly higher payoff. But if firm 1 does choose to advertise, firm 2 would not advertise because it gets a slightly higher payoff for that. So there's no clearly dominant strategy here. However, what firm 1? 6. So this is a dominant strategy for firm 1. Does firm 2 have a dominant strategy? Well, we can see here that if firm 1 chooses not to advertise, firm 2 should advertise because it gets a slightly higher payoff. But if firm 1 does choose to advertise, firm 2 would not advertise because it gets a slightly higher payoff for that. So there's no clearly dominant strategy here. However, what firm 2 can do is reason about what firm 1 would do. If firm 2 assumes that firm 1 is rational and self-interested, which, as you recall, is one of the assumptions. Now let's apply the idea of backward induction to a slightly larger game, or at least part of a game, of the game called tic-tac-toe, otherwise known as noughts and crosses. I'm only going to solve part of the game because the entire game would be too difficult to solve in a simple video and wouldn't fit onto the screen. But we're going to look at the start state where we're in this current game. Down the left here we have whose turn it is at each step, and the moves that we have, we've omitted the names of the moves, but you can see the moves here. For example, X is placed into this spot here, resulting in this new state. I'm going to solve from this state and show that from this state, player X has a dominant strategy that can win the game. Each of these states here also has a subtree, but I'm just going to show you that taking this move leads to a situation where X can always win, and no matter what naught does, they can't win. Let's have a look. So first we're going to start by solving the subgames at the bottom. The subgames at the bottom down here are quite simple because there's only one outcome. We're filling in the last possible spot. So in this case here, the subgame just has one action available. So we're going to backpropagate the value of that to the node above it. That's pretty easy backpropagation because there's only one action available. And those three actions are the subgame perfect equilibria for those subgames. Now we're going to solve the subgames that are available to naught at this level, of which there's two, this choice and this choice. So in this subgame, player naught can choose between a draw, payoff of 0, or a loss and a payoff of -1. It's going to take the draw. if it's rational and self-interested. And in this subgame, it's going to choose between a draw and a payoff of 0 or a win and a payoff of 1. It's going to take the win clearly, so the payoff will be like this. Now we have several subgames we've got to solve across here for player cross. These subgames here I'm not going to solve. I'm just going to show you that if agent naught takes this move down to here, it will win. If it takes this move down to here, it will win. If it takes this move down here, it will win. So there is a dominant strategy for each of them, and we'll backpropagate those values. While there are other moves, just to kit for time, I'm going to do this. This subgame here is a bit trickier. We've got a choice of 3 actions that we can take, playing here, here, or here. The one on the left leads to a win and a payoff of 1. The one in the middle leads to a drawing game, and the one on the right leads to a loss. So therefore cross is clearly going to take the win, which would be this one here. And we backpropagate that value, 1, minus 1. From each point we see here, that all the actions that are available to naught have the same outcome, that they end up in a loss, 1 minus 1 across here. So at this point, once we've reached this state, there's no way that naught can avoid losing, provided that cross plays its game properly. So in this subgame, it doesn't matter which action we take, we just got to propagate our value up and pick one of the subgames as our equilibria, and we get this outcome. And similarly, what we're going to say, if we solve these games here, it doesn't actually matter what the outcome is going to be, because at best they're going to give a reward of 1 to player cross, and it's going to choose one of those actions. So the outcome is going to be 1 minus 1. And again, we'll just choose this game as our subgame, perfect equilibria. So what we can see here is that we use backward induction to prove that from this particular state, if player cross takes this move, they end up in a position where they can win the game irrelevant of what naught does. The difference between this game and what we've seen previously is that we've got multiple levels here, but the process is exactly the same. We solve the subgames at the lowest level, backpropagate the outcomes of those subgames to the next level, and then we solve the subgames at that level. And we keep going backwards up until we reach the root node of our game, which is this here. You can try and solve the entire tic-tac-toe game using this, manually if you like, and what you'll find is that neither player has a strategy to win the game at the start. The best both of them can do is to draw the game. Backward induction is a model-based technique. We need to know the transition function in order to solve this backwards. But we can solve extensive form games in a model-free manner or a simulation-based manner using reinforcement learning. We define a stochastic game as something that's quite similar to an MDP, except that the set of actions, the transition function, and the reward all operate on tuples, just like we saw in an extensive form game. We won't go into detail in this video about the definition of a stochastic game. You can refer to the notes for that. But we will look at the intuition behind how we can use reinforcement learning to solve stochastic games. We can visualize a stochastic game in a similar way to what we visualize an Expectimax tree. Here we see an Expectimax tree earlier from the multicolored tree search notes. We have a state, we can make choices between actions. If we choose an action, there's some probability of going to different outcomes, and then from those outcomes we can choose further actions. In a stochastic game, instead of the outcomes of the actions being chosen probabilistically by the environment, we can model that the outcomes of the actions are in fact chosen by other agents. In this case, the actions with the primes on it refer to the actions that are available to an opponent in a two-player game. So in this case here, action A is chosen by our agent, coming to a new state called L. The dark states refer to the states where one of our opponents has a choice. Our opponent can choose this action A or this action B. From the perspective of the agent that chooses here, the light-colored agent, whether or not another agent chooses this outcome or not is largely irrelevant to how good an action this is. If we sample these enough times and we find that this agent selects this action 80% of the time and this action 20% of the time, then this is the same as the environment choosing it at 80% and 20%. The expected reward can't be calculated based on probabilities because at this node here, the agent that makes the choice between A prime and B prime is making the choice strategically. It's also trying to maximize its expected discounted accumulative reward. So therefore, from the perspective of the player that chooses here, it has to consider the strategy of the player that chooses after it, and in fact, all of the players that choose after it in this move when it's evaluating the strength of move A. But nonetheless, we can see some similarities between MDPs and stochastic games. In this case, the agent has to choose between A and B, and the outcomes that matter are these states for A and these states for B. It's actually largely irrelevant which action this agent chooses from the perspective of this agent. All that's relevant is the outcome that we get to. Whether or not this outcome is selected by another agent or the environment, we can still use reinforcement learning techniques to solve it. Multi-agent Q-learning is a multi-agent version of the well-known Q-learning algorithm. We can see the algorithm itself here on the screen. There are a few differences, notably that instead of getting an MDP as input, it gets a stochastic game with multiple sets of actions for agents and multiple reward functions. What we want to do is learn a Q function Qj for player J, which is the agent that we're learning for. We initialize this arbitrarily like normal. Then multi-agent Q-learning looks very similar to standard Q-learning. We have a series of episodes. We then select actions using a multi-arm bandit algorithm, execute those actions, wait to see the outcome, and update our Q function. The primary difference is in these 3 steps here.
So RefOS, you say, how do you choose on what to study? I'm in my final SC from guessing Melbourne Uni, and I feel like I haven't learned nearly enough about CS for a job. Wait, where is, unless Mech Uni is actually a thing. No, it has, is it? Yeah, it has to be Melbourne Uni, right? Alright, but firstly, Melbourne Uni, yo. Secondly, oh, oh, okay, a meh uni, okay, a not so good uni. I was gonna say, okay, I got you. Okay, so I mean, the question is that related to like per subject, or is it what to study before an exam, or else? Yep, so for a software engineering position, okay. Okay, right, so in that case, I'm guessing you mean like subject-wise. How do I choose on what to study subject-wise? For me personally, I've always picked the harder subjects. We're talking, we didn't need to learn about declarative programming, but yet I did learn about declarative programming. And there were some other subjects as well, but that's one example. During your bachelor's, there's always like a core set of subjects. If you have those core set of subjects, I reckon that should be at the minimum enough for you to feel like you're confident. The thing is, maybe it's all about just having personal confidence in yourself for this type of stuff, right? But I can't really say to your specific situation here, Raf or Ref, if that makes sense. Because the thing is, like, you also have to consider that you might not, you don't need to know everything before you go into a job, especially as a software engineer. And if you're currently in your final year, you should probably be looking for like grad roles or grad jobs, which, you can do, or you can just go work for some smaller company in the meantime while you skill up over the next 2 years or something. All right, always think in the long term in that respect. But there's always a place for you, is what I'm saying. And hello, Aditya. I hope that's somewhat helpful advice. I mean, if you have any more concerns, man, just tell me. Mm-hmm. Let's see.
The first thing we have to do is when we execute the action, instead of observing the state S prime that we arrive at, we wait for the other agent's actions, either by simulating them if we're using a simulation environment, or via letting them play their moves if we're using a completely model-free environment. We then observe the rewards that we received over all of those steps that all the other agents made. So we can receive a reward for playing our move, but we might also receive a reward, positive or negative, when an opponent plays one of their moves. And we also observe the new state that we arrive at, which is n moves later, where n is the number of players that take their moves. Then the update rule looks pretty similar. We're updating q of j, where that's our q function. We do it by updating the old information plus the weight of alpha times by our new information. And our new information is exactly the same, except we have to remember to sum up all of the rewards we received since we played that move. Note that the temporal difference value is st plus n, which is the state we observe after we have waited for all the other agents to play their actions. So this is effectively exactly the same as Q-learning, except instead of executing action A and then observing the new state, we have to wait for all the other agents to play their move, observe that state, and then use this rewards that we received along that path to update our Q function. Multi-agent learning works quite well. However, we can improve things by being strategic about the way we simulate opponent moves. So as we can see here in this example, when we take the selection A and execute it, we wait for the outcome. However, if we're in a simulated environment, how would we simulate an opponent's moves if we don't know who that opponent is? There are a few different strategies we can use in order to simulate a good opponent that will improve our learning. The first strategy that we can use is to just do random selection. This is quite easy because we don't have to think too hard about what our opponent's going to do here, and we just select uniformly between A and B. While it's easy, the problem is that
So do you think it would be good enough if I became really good at technical interviews, but might have some gaps in my knowledge at the further stages, or do I need to know more theory as well? I think it would be good to balance it. Okay, so maybe you can say practice for technical interviews 60% of the time, and in those 60%, in the rest of the 40%, you learn about the different DSA that you're currently studying. But I mean, the thing is, like, what do you think you don't know enough of? Right, so give me a few examples of, say, the things that you think you're missing an understanding of. Because I guess before you even know what to start on, it's probably good to know what you're missing. But also, it gives me an idea.
that may end up exploring a lot of actions that will never be taken by a good opponent, and therefore we'll get a very poor idea of what a good Q value is for action A and action B. So for example, if a really good opponent would only ever choose action A, but we simulate that the opponent will choose action B 50% of the time, and B is a really good outcome for us, then we'd get a really poor idea of what action A is. The second thing we can do is use a fixed policy. So we can use an existing stochastic policy that gives reasonably good behavior of the opponent. So for example, this could be a hand-coded version of the opponent or a policy we've learned from a similar game. If we use a hand-coded fixed policy, we could determine that action A is a really strong policy for this agent, and therefore would simulate this more often than we'd simulate the weaker action B. And this will give us a better idea of what the true Q value for action A is. Of course, this is difficult because if we already have a really great policy for our opponent agent that's been handcrafted, presumably we can usually come up with a very good hand policy for our own agent, and this would defeat the purpose of using reinforcement learning at all. So usually a handcrafted policy or a fixed policy is a reasonably good policy but not a great policy for the particular stochastic game we're trying to solve. And we can use Q learning in order to determine a good policy for this player. The third type of strategy we can use is called self-play. Using self-play, we can simultaneously learn a policy for both ourselves and our opponents. And when it comes time to choose actions for our opponents, we use the policy that we're learning. If the action spaces for both ourselves and our opponents are the same, such as in games like chess and tic-tac-toe, we can actually learn a single policy and have both our own agent and our opponent's simulated agent use that policy. This is a technique used by, for example, AlphaZero for learning how to play Go, chess, etc. If the action spaces aren't the same, then we actually have to learn separate policies for each of the agents. At this node, we would use the policy for agent J, for example, and this we would use the policy for agent K. But the important thing is that the better that we can simulate the quality of these moves for our opponent player, the better our primary policy, which is the one we really care about, is going to be. Just as we could extend Q-learning or SASA to a multi-agent case, we could also extend Monte Carlo tree search to a multi-agent case with just a small change in our algorithms. Multi-agent MCTS is similar to single-agent MCTS, but we simply modify the basic MCTS algorithm as follows. Recall that the first step in MCTS is the selection step. In the selection step, we have to select a node to expand in our tree. At each point, we choose an action based on the current policy that we have using stochastic multi-arm bandit algorithms. When we select for our moves, we can use our policy in order to select this. But similar to when we are waiting in multi-agent Q-learning, we have to also select for our opponent agents. We can do this using opponent simulated play that we saw in the previous video. That is, we could either select randomly, which isn't going to work very well, but it's very easy. We could use some sort of fixed policy to choose for our opponent, or we could use self-play. In multi-agent MCTS, we know which player's turn it is at each point, and what we have to do is use a multi-arm bandit algorithm to choose an action for that player, irrelevant whether it's us or one of our opponents. The second step is called the expansion step. When we're expanding a node, we would come to this node, which is our node here, and select one action randomly. This would lead us to a node that's a choice for one of our opponents. Unlike in single agent MCTS, where we then choose an outcome probabilistically, all we do is simulate from this node, get the outcome of the simulation, and backpropagate the value. We don't bother choosing an outcome from one of our opponent's states. However, on a subsequent iteration, we might select this node, which has no expansions. Then what we do is randomly choose one of our opponent's actions. Okay, and this will lead to an outcome that might be, for example, a state where we have a move, and we simulate from that. So in other words, different to single agent MCTS, where we would choose an action and then expand one of the outcomes, all we do is choose the action, result in a state, and do a simulation from there. In future iterations, we effectively simulate the outcomes of our opponent's actions by selecting these nodes, expanding them, and simulating further. The next step is to do the simulation. This step's much the same as before. We simulate a random simulation from the most recently expanded node. The only difference is that we have to remember that the rewards we receive are going to be a vector of rewards, one for each player, and so we have to update the right Q function using the right reward from that vector. The final step is the backpropagation. The backpropagation step is the same as before.
So we're lacking in discrete maths in general, but data structures are right, not great. Algorithm knowledge is similar. Thing is, discrete math, I think you don't really need it that much, right? That's one thing. If you think you're all right in data structures and algorithms, like if you, like for me, I thought I was alright, you know, that, but I guess I got like a half glass full type of mindset. Like I thought I was alright and I could be able to solve the Leetcode problems if I just revisited the ideas a little more, which is what I did, you know, which is what I do. Revisit the ideas. Anyway.
Except we have to keep the value of each node for every player if we're using self-play. So in other words, we don't just update the Q values for the player that we're learning for, we update the Q value here for player K and also for player J, which is our player. This allows us to then use this Q function for the selection steps in the next iteration. An interesting application of reinforcement learning as applied to extensive form games, in this case imperfect extensive form games where some information is hidden, is the poker player that was written out of Carnegie Mellon University. This is an interesting application because unlike Go, where the game's fully observable, poker has some unobservable parts of the game, for example, the cards that our opponent are holding and the deck of cards that are here. Further to that, we have situations where players can do things like bluff about what cards they have in their hand. What was interesting about this application is the way they used abstraction to solve the game. So when they took their original game, and this triangle here represents, for example, the game tree that they would have to solve, it was far too big to solve using something like backwards induction. What they used was an abstraction algorithm that extracted down to a smaller game. So for example, one of the simple abstractions they used was when you have to bid the amount of money you're prepared to bet. This could be a number in dollars up to a certain amount, and what they did was just bucket those numbers together. So instead of having an action for betting $1, $2, $3 all the way up to the maximum bid, they just
Getting an Amazon internship is not just alright. Yeah, arguable. I mean, yes, it isn't just alright, but I don't think that necessarily needs to correlate with how well you know an algorithm, right? I guess the question is like, if you think of a heap queue, if you think of a priority queue, what is the data structure that you think of? A heap. That's the level of like understanding that I had when I first got into doing these Leetcode problems. In the sense that I just had a high level of understanding on it. And technically that's all you need for even building the algorithm. Just know a few high level concepts. You know that your priority queue must use a heap. Search up on Python, search on like on Google how to implement a heap in Python. Yada yada. What's my age? 21. But like what? Another example. Binary search trees. I'm thinking, okay, what makes up of that data structure? It's a tree. It's a binary tree, meaning that there is two children. Right, so this is like something that I would have thought of before I even started learning Leetcode. Alright, that would have been at the back of my mind. Maybe I wouldn't have articulated as well now because I've done so many questions on binary search trees. Actually on binary trees, more than binary search trees. The difference is a little bit nuanced, but you have to know it. And that's only something I knew after I read up, done questions on binary search trees and binary trees. right? Having done these two different types of questions. But before this, you know, I would have probably had trouble identifying to you what is the difference between a binary tree and a binary search tree. Right? And the only reason that I got better was because I did more Leetcode questions and I realized, okay, a binary search tree must have the numbers in a particular order. Whereas in a binary tree, there is no enforcement of that rule. And then I can delve a little deeper into that if I have to. But just have like a general idea of these data structures in your head and algorithms in your head. Don't need to remember Dijkstra's algorithm. You don't need to remember like all of these specific algorithms, at least for technical interviews. What, like Dijkstra's like, oh, what was the other one that was like very, there was one that was like an offshoot of Dijkstra's algorithm. Bellman-Ford, yeah, Bellman-Ford algorithm. So Dijkstra's algorithm, Bellman-Ford algorithm, you don't need to know these. But you might need to know the underlying data structures of those algorithms. Maybe for Dijkstra's, it's probably like a priority queue. Bellman-Ford, I don't know, probably like a dynamic programming. And the only reason why I say Bellman-Ford dynamic programming is because I only know of this specific, like I don't remember Bellman-Ford at all right now, but what I do remember from just taking a semester today of this subject that I'm currently learning, that something about Bellman-Ford, something about dynamic programming, Bellman-Ford, but the Bellman-Ford approach is the dynamic programming approach. That's all I remember so far of this, from this subject, which I am currently taking. Right, so broad idea. Keywords, dynamic programming, Bellman-Ford, okay. They link together. Keyword, Dijkstra algorithm, heap queue, or I mean priority queue. Priority queue, and then links to heap queue because it's Python. And no, Dijkstra's algorithm also links to graphs or something. Same with Bellman-Ford equation. I feel like this is, I'm pretty much just like describing nodes in a graph, similar to like the Obsidian graph view. Similar to this view. I feel like if I search graph here, can I search a value? Search files. Let's not look too closely. So you can't really say anything specific there. Right. $11 years old plus 10.
bucketed them together and said bets between $10 and $15, for example, are effectively the same. They use several other more sophisticated abstraction algorithms, but in the end you have this smaller game that we're going to solve. They then used a custom algorithm for finding the Nash equilibrium of this game. However, this game, despite being much smaller than the original, is still far too big to solve using backward induction. This custom algorithm used a lot of Monte Carlo simulation techniques in order to come up with the Nash equilibrium for this game. Unlike solutions like Go, for example, though, they actually did find a Nash equilibrium, and they had certain guarantees around the acronym and the original. Go on for simply zero, which are more or less multi-agent Markov. In this section, we introduced the notion of extensive form games, which are more or less multi-agent Markov decision processes that can be generalized into something called stochastic games. We learned about backward induction, which is a model-based technique for solving extensive form games that finds the sub-game perfect equilibria of each sub-game and then uses that to solve the parent game. Backward induction is model-based.
FOS, you think you got an idea on how to tackle this? Nice. Yeah, nice. Honestly, like, for me personally, you know, I think that I always think of, you don't need to know algorithms to depth. I mean, you do, but not always. At least for a software engineer, you don't need to have memorized Dijkstra's algorithm. You don't need to have memorized how to even do a heap queue implementation in Python or a priority queue implementation in Python. You don't need to know it. But I mean, doing more Leetcode questions, you do end up knowing it more, but you don't need to. And that's just the power of knowing that you don't need to. You're not limited by your own, I guess, flaws. You don't think that, you know, you have to remember things, because you know when it comes to being a software engineer, you know you can search them up on the job. And if anything, the best thing you can learn is how to learn. But I think also, you know, yeah, I think another thing that helps me is realizing that as a software engineer, you don't need to know everything, because you can search it all up. Right? It's not like you're a doctor, where you do have to know everything. Kind of on the spot as well, if you're like doing surgery and you don't know what you're dealing with. I mean, that just comes from practice. Same thing, I guess Leetcode is like practicing your surgical operations, but with code and words and a screen rather than tissue of a human body. But I would bet, like, if you do just Leetcode questions, you'll also gain a lot of confidence there as well. So just do some, you know? Like, literally, don't worry about, like, if you feel like, you know, discrete maths is one thing that you're not sure about, you don't really need it that much when it comes to software engineering, so don't worry about it. And then your data structures and algorithms, just do Leetcode or Neetcode 150. Okay, I think I've hampered on enough.
But we can use model-free and simulation-based reinforcement learning techniques to solve extensive form games as well. We looked at multi-agent Q-learning and multi-agent MCTS. So these techniques can be improved by making informed choices about good opponent moves, such as using self-play. Most importantly though, we saw that multi-agent reinforcement learning techniques are very similar to their single-agent versions. requiring just small modifications to successfully solve extensive form games, but often these require a lot more computational power to solve successfully.
Oh, look at the traffic.
Okay with that?
Sorry guys, that was the alarm. Which signifies my 18 minutes today spent on just updating my scheduler app a little bit. So I'll just tidy things up now. I'm gonna say I should spend some time on scheduler, just saying there's no excuse not to. If I've been doing like an hour or two on Leetcode, like I could spare 18 minutes. Man, I'm lagging as fuck. Shoot, man, this loads forever. I need to open VS Code on a different computer. That's what I gotta do. Love this Patrick guy, he made a good contribution. Wait, that's only one file? Right, because... Okay, and so that is this one done. I want to I think this one is easy. This is simple. Yeah, just to remove that. So that's fine. Add DB health check. So this is gonna be only one file. Okay, yeah, Docker Compose. Now I might do this on a different branch. So I'm going to open up Microsoft app. Microsoft app? Wait. Okay. I will do this. So Windows app is what I'm looking for. Now that'll log in. While that logs in, gotta think about this one real quick. We're just adding a health check for the database, which is cool. It is indeed pretty cool. CD. So WSL. .exe. We're going into scheduler, and we're going to code in scheduler. New VS Code server download. Okay. Now, we just need to add this health check for the DB. Right after the restart. And this is on, depends on DB. Where is this? This is adminer? Is this adminer? Or is it backend? It is backend. Okay. Done. Simplify traffic, remove www redirects, which add complexity. Okay, well, I'm not going to worry too much about that yet because the maintenance so far is cool. I think I've done enough maintenance now on this. Let's close this, close this. Now we can say that we've done the lecture. Where is it? APA lecture, we didn't even write it here, okay. This is the APA lecture, that is done. Now we can quickly just look over the tutorial. I think I'm freshened up now. To say we can go look at the tutorial, but before I do that, let's create a PR just so we are catching up. New PR. This is maintenance. Changes from dhrov, derov. Hello, man. Now, base branch should be main, and we're going to create a draft. Or there is good news for you, can I tell you? For sure. Go, tell me. Reload window. Alright. There was update to front-end client, which I'm just gonna not bother keeping. We can close this and reload. And that'll be just another pull request that I'll be working on. This was never really changed, so we're not going to worry too much, and we're going to close it now. And let's just check some of these messages. People and culture. Cool. Bet. Thereof, thanks, man. Yeah, man, that's what I'm here for, you know? Hopefully, you know, we can all work together. Some wholesome shit, you know what I mean? Some real wholesome stuff. How to get good at life in general? I mean, that's a broad topic. The real broad topic there. But if you want my take on it, let's see if it's a mature or immature take. So, how to get good at life? Honestly, to me at least, I would say one is to set good habits. And honestly, if it's to set good habits, like that's pretty much all you need to start out. Then number two, maybe 4 years later, which is the exact amount of years that it took me, find your passion or find your motive in life. Find what drives you in life. Now, what drives me in life? That's a good question. I'd say it's really, for me at least, to be able to learn something and be able to provide value back to the people, to people like me. So, you know, part of my goal in life is just to bring value to the world, right? That's the bio in my LinkedIn. Live to learn, or was it love to learn or something? And bring, fuck, I forgot, wait, what the fuck? Yeah, bring value to this world though. That's the main headline. Okay? I'll go to my LinkedIn anyway. Live to learn. Or something else. Live to learn. Just happy to bring value to the world. Yeah, right. Love to code. Live to learn. And just happy to bring value to the world. Okay, that's my kind of like my passion, right? That's my motive. That's my ethos. And then how I get to that ethos, how I get to even thinking about this stuff, I think you just need good habits to begin with. And to reduce the bad habits. For me at least, my bad habits, they're not necessarily bad, right? But I played video games quite a bit. We're talking Valorant, yes, of course, right? We're saying I played Valorant for like 3 years straight. You can find like a whole stream, a whole archive of streams which I just did Valorant every day for at least like 2 hours. And then I just decided it was like I wanted to do something else. In the sense, I kind of got my motive and then I stopped playing Valorant. But still, the Valorant that I did play was like consistently time boxed in a sense that it was also a habit that was consistent. Like I didn't not play Valorant, so that was also kind of odd in a good way. But look, I decided I do find more enjoyment in building something than I am playing Valorant. That's just me personally though, right? Like, the gamer, look man, you are the gamer, so, you know, maybe it's part of your identity. Which, talking about identity, that's what Atomic Habits is also about. The book, Atomic Habits. If you do the habits which match your identity, or don't do the habits which don't match your identity, then you become, I guess, God. It's probably not God, you know, but whatever, you get me. You live in USA? No, I live in Australia. And right now it's meant to be 30 degrees today, but I'm kind of getting cold. Kind of. I will say. But yes, how to get good at life, that's my answer. Although long-winded, I mean, yeah, the answer is get good at habits, do them well, and sooner or later you'll find your motive in life, because all the problems of habits, you're just like, you've mastered them. Right. Are you originally from Australia? I am born in Australia, yes. But my family, they're from, yeah, I'm like the first gen Australian. I mean, first gen Chinese Australian. So, first one here that was born here. That's me. For our family. Anyway. Let me have a quick look. All right. So, the problem of the workshop. All right, let's just do this because it's right in front of me. All right. List 3 general approaches to deal with replay attacks. The 3 approaches is 1 to use a timestamp, 2 to use a nonce, and 3 to keep track of the nonces. Now that's a problem. I need to remember that. I need to remember the 3 different ways. Okay. Gaurav, what is the recommendation for someone starting out at coding? So I would say learn Python, then learn C, which is, okay, by the way, I'm saying this because this is how I did it. Okay, but I actually agree with how I've learnt it so far. But, you know, I would learn Python, then I would learn C, and during the process of learning both Python and C, learn about data structures and algorithms. That should take about, maybe, like, if you can be quick about it, you could do this in 4 months if you really wanted to, but you could also do this in a year. All right, if you're really proficient, you would do it in 4 months maybe, but you might rush through it. But in a year, you can probably definitely get through all data structures and algorithms, at least the common ones for Python. And you can do them all in Python, right? You don't need to do it in C. The point of learning C is to learn about pointers, addressing, low-level programming, right? The point of learning Python is to learn high-level programming language, because that's what Python is, a high-level programming language. C is for low-level machines. C is what I think Linux is written on, maybe. Okay, I could be spitting dumb shit right now, but say maybe like hardware, right? You write code for hardware generally in C, or more recently nowadays it's Rust. Regardless, whatever. Side tangent. Anyway, after you learn Python and C, after you learn about data structures and algorithms, you know, if you can in the process also learn about Leetcode and do some Leetcode problems, and you most likely want to do your Leetcode in the high-level programming language, that is Python. But more I guess the competitive programmers like to do it in C++. Now, if you know C, C++ is not going to be that much harder to learn. And yeah. Okay, the gamer says C is not a low-level lang. All right, well, you're going to flip my world upside down. Hold on. Okay, is this a level of debate that is this Oh yeah, so Gurav, Gurav, you have a good point, right? Why do DSA? Can't you just go to development after learning the basics? You're very right, right? That's my thought process as well when I first started. Okay, the only reason you want to do DSA heavily is if you want, say, a tech job in the future, in big tech, right? So if you have solid foundations in your DSA, you will have a solid, you'll be a solid candidate for, you know, either internships or grad roles for big tech companies. That's the general idea why you want to learn your DSA well. But not only that, you do build this confidence in your skills as a software engineer, or as a programmer, as a coder. But it's also good just to know in general, because when you think about Python, they have this thing called the dictionary, right? How do they create this dictionary data structure under the hood? Having some knowledge of how this data structure exists under the hood for Python, just at a high level, right? You're saying like, okay, I know a key gets hashed to get this value, and it's only this efficient because the key is being hashed to find a value, right? That type of understanding is what you need to have, just in general. And yes, you can go to development right after. you just learn the basics, which is like what most people do, like what I did. But you also want to make sure you are learning your DSAs for efficiency and shit. So in the future, you don't like just do 2 for loops and call it a day. And then you have low efficiency in those 2 for loops, and production code is, I don't know, running bad. I don't know. Running longer than it should. I mean, that's like a really, like the chances of that being a problem that you really face is probably slim, because you're probably going to be coding, fixing maybe, I don't know, it could be if you're doing front end stuff, then there's none of that, none of this time complexity stuff you need to consider. Anyway, hello Aditya. But okay, this, is he a low level or not? Context dependent. I mean, okay, yeah. Yeah, right, that's fair. I mean, it's low level in the context to which we are talking about it. So if we're talking about it in comparison to Python, well, that seems pretty low level to me. Long time no see indeed, Aditya. Gaurav, so how many years you were living in this world since you were born? You could just ask how old I am. I am 21. Okay, so list 3 general approaches. I listed 2. You needed a timestamp or a nonce, but you could also use something else. There's a third one that I need to remember, right? And so this is a problem that I also want to remember. If I go to cryptography, move it to a new tab. Now, we are looking for, so the 3 general approaches to deal with replay attacks. So what are the general ways, what are the ways to prevent replay attacks? I know 2 of them. The third one is a challenge and a response. No, that's a nonce, right? That's a nonce. Attaching a sequence number. I totally forgot about that. Okay. Okay, attaching a sequence number prevents replay attacks for sure. It does. That's the simplest one that you can think of. So what are the 3 general approaches to dealing with replay attacks? That's a good answer. So attach a sequence number, party A accepts a message fresh as a timestamp, and yeah, and then expecting a fresh message as a nonce, and then yeah, that's exactly it. So people feel weird if you directly ask their age. I mean, that's fine by me, to be honest. Fine by me. The gamer, I'm getting confused. Some say C is a middle level and assembly language or machine language are actually low level. Now, the thing is, who writes an assembly realistically? The problem is nobody does. You know, there's some people that do, but the chances of people actually using using assembly for low-level programming, I mean, it takes balls, is all I can say. But C is just one-up assembly, which is higher level to assembly in comparison, but is low level to Python, because guess what? Python is written in C. You know, you can say assembly was probably written, sorry, C was probably written in assembly. Maybe, I don't know. I don't know. It's I was bullshitting. I don't know if it's true, but it is true that Python was written in C. So what keeps you away from social media or any kind of distraction? Well, for one, this is pretty helpful. You know, my phone is literally my camera, so I can't use it, right? That's one reason. But I also do this thing with my phone where it's got this app called OneSec, ONE space SEC, OneSec, right? OneSec, which does this thing to my apps that I specifically tell it to do. And it does just like every time I try to open the app, it rejects me from opening it, and then you have to wait on the screen for like 10 seconds before you can actually jump back into the app. And I do this for like Instagram, I don't know, YouTube, some other ones, but I forgot. Reddit. All right, so these three. There's one more, I think. LinkedIn. I actually do it for LinkedIn as well, because sometimes I actually look at LinkedIn too much for my own good. Okay, Kevin. So what rank were you the last time you played Valorant? Do you also live stream on this channel while playing Valorant? I don't live stream on this channel playing Valorant, but I did on a different channel, which is called Subwoofer. Okay, but it's like so unrelated to my, I guess it's not even linked very, you know, tightly to this YouTube channel. But the last rank that I was in Valorant was Ascendant 1. That's as much as I got to. I think I got to, yeah, I definitely got to Ascendant 2 in the past, but then I became washed, stayed in Diamond 3 for ages, and then reached Ascendant 1 and just quit. Okay, I didn't quit, I slowly just didn't play it much. I'm not saying I've quit it just yet. Okay. What is your high school GPA? I don't know, because I don't know what the equivalent GPA is for high school. But what, top 8%? I think that's all I can say. It was definitely it was like top 7 to 8% of the entire cohort. Unfortunately, not top 0.05%. Unfortunately. Anyway, boys, I will have to have dinner now, and I'll be back in about 30 minutes to just continue on with these questions. I will say, yeah, I guess before I do that, let me understand this question in full. Right, so party A accepts a message as fresh only if the message contains a timestamp that that in A's judgment is close enough to A's knowledge of current time. This approach requires that clocks among the various participants be synchronized. Yeah. Attach a sequence number for each message and use an authentication exchange. A new message is accepted only if its sequence number is in the proper order. I agree, and party A expecting a fresh message from B first sends B a nonce challenge and then the correct nonce value. Okay, so these are the three different replay attacks, right? So this is something that I will have to say. In the cryptography notes that I have. So this is going to be here. Yeah, let's do it here. Okay, and you know, it's going to be sequence number, right? I got to remember the term sequence number, timestamps, and challenge response. Alright, these are the three that you just need to remember. Sequence number. So if you think about it, replay attacks. A replay attack. A replay attack can be blocked with sequence numbers, so A, B, C. So as soon as you walk into the room, you see ABCs, or maybe just 1, 2, 3s, and you see a timestamp, which you see a clock right above the numbers. And then there's also challenge and responses, which maybe is just an image on the wall on the side for a challenge and response. Okay. When I come back, I'll remember this. I would have remembered this. And I will say that, so that's that question. That's the second question. They're done. And we'll understand these questions now. Hello, Zahib. Can you share YouTube channel where you played Valorant? For sure. Alright. Subwoofer. Subwoofer. We have TikTok. Here we go. Should be it. Here we go. This is the channel. Hello, Shivam. Hello, Shivam. This is the channel for my Valorant. We're talking 926 videos, each at least 1 hour in length. Okay, so these aren't. But if I go to live, we got a catalog of 926 streams that last between 1 game to 2 to 3. But there you go, if you want to check it out. Are you studying security? I'm studying cryptography and security. That's one subject name. But yes, it's pretty fun, I will say. It's pretty cool once you understand things. So you're literally off from Valorant until undecidable. Yeah, at the moment. Bros and Minecraft bros. I don't know what you mean by that, Zahib. I didn't play Minecraft much. I mean, I did play Minecraft quite a bit actually, but that was before my days of Valorant. Alright guys, BRB, I am going to just have some dinner now. Alright. I'll put on some music and I'll be right back. What do you mean bro is playing Val IRL? I'm playing the game of life IRL. Probably. Okay. Back. Vibav. So what tech stack do you know and where did you learn it from? I'm basically just copying the tech stack that I'm learning. And then just going backwards or working backwards in the sense that I'm at the code, let me learn what I am looking at. But the tech stack that I am using is unconventional, right? Or it's not really, say, the MERN stack or some other, stack. It's Fast API, Postgres, Node, and React. Fast API, Postgres, Node, and React. FPNR. So I don't know. I don't know what that acronym would be, but FPNR. You nice. Hello to the new 2 people that joined the Discord. Okay. Alright, now let's consider these 3. So consider the mutual authentication proposed by Wu and Lam. Actually, my hands feel a little sticky. Give me a sec. I'm gonna just quickly wash them. Be right back. Okay. Give me a sec. Okay, so can be reduced from 7 to 5 steps. Show the message transmitted at each step. The final message in this protocol is the same as the final message in the original protocol. Show the message transmitted at each step. The final message in this protocol is the same as the final message in the original protocol. Okay. Well, let's see what's at each step, alright? What do you know at each step? So A knows ID A and ID B. KDC knows ID A and ID B. B knows ID B. Technically also IDA. So they all know everything. Except, we'll say this is likely to be, so look, at A, that is that. However, at 0, we're going to have IDA, BC. IDC has nothing. IDA has this. IDB has, so A, KDC, and B. Wait, hold on. Shoot. B to KDC, sorry. KDC to A. PR auth. IDB, PUB. That's sent to A. IDB with PUB. Technically, it's like IDB is acting as a nonce in a sense. Maybe. PUB is the public key of B. Public key of B. Now that's assuming that PR auth. That's assuming A know what PR auth is. I'm guessing then PRB would also know what B would know what PR auth is. Non-survey some IDA to B. So only in the B step is A getting PUB. So I'm just going to say this is what they get. C. Oh well, that doesn't work. Oh. P what? Yeah. Oh my god. I mean, technically I can think of it as just this. All the stuff that will get. A is just. Oh yeah. And A gets PUB there. B, KDC, B. So ideally E gets something in B. B is gonna get IDA, PUA, both. I guess it doesn't know PUA, does it? PUA, as well as what to be sent to A. Can't decrypt that personally. So you will decrypt it. You would send it you would send it to A to decrypt. So B has NA and PUA. He gets N of B. B can decrypt to get the right value. But A is N of B, and then N of B. You have N of B also. B doesn't really learn anything new. But NB and NAKS Wait, does B know KS? I don't think B knows KS. Am I wrong? B knows NB already. NA and NB. So the protocol can be reduced from 7 to 5. Show the message transmitted at each step. The final message of this protocol is the same as the final message in the original protocol. From A to B, step C. Should be an A, I think. I might make this red, make this red also. KDC. B to KDC is D and A. KDC to B is E, which is BUA. B to A is NBKS. AB is nothing. I think that's right. Oh, interesting. This is just the same protocol. Yo, that's actually massive. But what is the trick here? I also got this message. Simply detecting whether the message is modified or not can be achieved by digital signatures. You can still achieve some level authentication to bind a key with an ID. What are we even talking about in reference to? Simply detecting whether a message or not, whether the message is modified or not, for integrity, is achieved by digital signatures. Prime job over KDC. Ah. You can also achieve some level of authentication to bind a key with an ID. For example, two parties can share the key face-to-face. However, one party can always deny the ID of the key to others because others cannot verify it. but it is not the case if there is a public certificate that others can access. So you can still achieve some level of authentication to bind a key with the ID. I see. Face-to-face, however, one party can always deny the ID of the key to the others because others cannot verify it, but it is not the case if there is a public certificate that others can access. Right. Okay, sure, I can understand this. Thank you. Thank you, Zenji Lai. This is good explanation, but I will have to rewrite it in my own words. That being said, also, I should go to exam revision and just say here when we zoom in, so authentication, there is some authentication still possible without KDC. Integrity is that would be the job of digital signatures. I think that's the main 4 concerns. So thank you, Zenji Lai. I will say, so that's fine. Okay, so non-repudiation was the answer, which I gotta use a different color for. I don't know what the B one is. Alright, doesn't matter. Going back to these questions, so we will have to look at the solution here, which should... Okay, well this is the solution actually, this doesn't give me much else. So I guess I gotta understand what B gets here. B gets NA in the first step. Oh, I see B gets NA. B to KDC gets NB. NA as well. KDC to B gets PUA. KDC to B gets PUA. Yeah. As well as... Yeah. And B to A gets... Gets the nonce for B and the KS. Yeah, it does. And then lastly, it just does the same step. Nothing. Alright, yeah, that makes sense. This makes sense. Now, why it makes sense is because just of the fact that these correlate or match with List 3 typical ways to use a nonce as a challenge. Three typical ways to use nonce as a challenge. What, you hash the nonce or you pass it through a function? Or you just use the nonce itself, or you use a nonce to... No. Yeah, no, I think we need to find this solution. Suppose NA is a nonce generated by A and B share K, and F is a function. So A to B is NA, B to A is... the Valorant question, yeah. Oh, yeah. Oh, I told them all about it. Encryption of a key with NA. So you just send the NA back, right? And then, or else you encrypt with a key to give to B to decrypt and send directly to A. Or you encrypt both sides. Well, that's definitely not what I expected. It's not what I expected as the 3 ways. List 3 typical ways to use nonce as a challenge. Well, that makes sense, but also I didn't realize you could vary the encryption aspect of it. So cool. From a web API security perspective, what are the drawbacks using HMAC? Please present an alternative to HMAC and discuss its benefits in web API authentication. HMAC is going to be interesting. Okay, from a web API security perspective, what are the drawbacks using HMAC? Present an alternative to HMAC and discuss its benefit in web API authentication. HMAC requires shared keys for verification, use of HMAC by API gateways or edge gateways, which perform the verification results in the need to store the MAC key. What? I'm reading wrong. HMAC requires shared key for verification, use of HMAC by API gateways or edge gateways, which perform the verification results in the need to store the MAC key, at least in memory. Alternative approach, given the structure of JWT, is to use digital signatures whereby the signing authority manages the private key, but the gateways perform token verification using public keys. The use of digital signature introduces a computational cost in comparison to HMAC. Well, that is something I gotta read up. So here's what, right? HMAC and MAC. Both stuff that I need to revise on partially, because this answer is interesting and I need to make sure I remember this for HMAC specifically. I should say scheduler development on the title of this. Live control room. Edits. Updated the title to also include scheduler development because I did do that today as well. I will say though, I've done enough of that. Done enough of scheduler development. Honestly, say in the next 10 minutes, plan tomorrow well. Okay, so you did the tutorial for CS, which by the way, I didn't even write here. Did I? I did, but this is actually set as CV, but it's CS. So when move to CS, that's done. CS lecture 2, week 12. That's not done. And we got these CV lectures, which I gotta catch up on. I just gotta check also, say, the calendar, or at least check the countdown. Ooh, I haven't downloaded countdown. Sus. Alacrity. We're gonna download it via the terminal. Mass install count down. Okay, mass search count down. Countdowns? Could be it. Nope, this is not it. Nope, that's not it either. That's not it. I'm surprised that it's not. Up here. Widget and counter. This is what I needed. I think this is the ID anyway. So widget and counter. I can probably turn off, oh, yo, look at this. Need my Bitwarden. I'll move this to the other screen. Favorites. Close. Close. Cancel. Ooh. Download last compatible. Interesting. Maybe this app is dead now. Except I still use it. For a lifetime for $10. Download failed, the installer could not be started. Well, that's no good. I wonder if it'll error again. If it does, then I'll just go to the App Store directly. It did fail. But why? Oh, is it because it's for the iPhone? Countdown widgets. Huh. I'm surprised it's not even here. Oh, here it is. Okay, designed for iPad. It is only for iPhone and iPad. How do I restore my purchases? TLS, privacy policy, Instagram, Twitter support. Hello. Maybe we're just gonna reset. Wow, having no countdown timer. Kinda sad. I can't even restore my purchase, like, this is saddening. What happened? And I checked all the, oh wait, unless it's unless Nope. Touch alternatives. Oh, that's not working. Oh wait, this is birthdays. Where are the other apps? I just realized after so long. He doesn't have one here. He just legit doesn't have one. It's not here anymore, is it? Oh. Who made this? Cranberry apps. So did I download like a clone just before? It's gonna be sus. Gotta go back. Where are the apps that I downloaded? I already have it. Need a refresh. Shit, 4 days? Oh my. Okay, no, we're fine. 29th, and then 8 days of AI planning for autonomy, and 4 days for computer vision. That is not bad. That is not bad. Well, that doesn't need to be full screened. So, looking at that, to me it seems my biggest need... Let me move this out the way. When is going to be someday... Oh, fuck. I gotta do this ASAP. I probably gotta do that pretty soon. Yeah, it'll be a lot more cryptography and security learning again tomorrow. I think what I'll do is I'll try and do more of these questions. Ideally, I can finish, so I finished all this. I'll close that now. And close this now. I want to finish more of these questions. Do at least, yeah, some more of these. Be familiar with these well enough so that I can do these questions. And it means that, you know, that would mean exam paper 2, 3, 4, 5, 6. Yeah, I don't need to tick them off. Just exam paper for Yes. And then those math extension questions are going to come in clutch because they're probably going to be pretty damn important. The tutorial APA can be done, if possible, tomorrow as well. Understand MST solutions, well, that's still, I literally put it from week 6. That's probably what I gotta do. Prep for relocation, well, there's really nothing else, is there? Yeah. How do I go back? Let me look at the logbook for a second. Okay, let's look at day. Exam paper. Exam paper. We're gonna move these two upcoming bots. These should be moved further. So CV, at least one a day could be ideal to get it through. Yo, how many CVs am I missing? Am I really missing CV lecture 2 week 10? Week 10 doesn't have a lecture, so no. This is week 11. Has to be week 11. So week 11. So every day, the upcoming weeks is ideal up until Saturday. However, scheduler development, I would say I did do that today then. So today, oh, it just doesn't show up, hey? Doesn't show up on the logbook anymore. Relocation, preparation, that's still something I'm thinking about. These things have to be done tomorrow, but relocation prep is still today. These can be reordered a little bit. We can move this here. Is this viable? Is this viable? It seems pretty viable. One exam paper question. At the very minimum, right? Leetcode at the very minimum. One exam paper question, and then you will have exam paper to do again, more, okay? CV, is that viable? Because what, by when do you want to have lunch? Right, when do you want to have lunch? When do you want to go to the gym? You can have lunch. Yeah. We'll still go to the gym, right? Lunch tutorial. Now, thing is, I might have to do this after lunch. Might do the tutorial here just because it should be relatively quick, like 40 minutes. That means we still have a lot of time to go through, maybe even 2 exam paper questions, 1 Leetcode question. Gym, lunch, math questions for mid-sem break from CS, and then a lecture from CS. Exam paper, well, if we can, but so it does seem to me at least that we won't be able to accomplish, say, this CV. So we're gonna say move that to the next day, move this to the next day, move this to the next day, I move this to the next day. Right. But that's looking to be my schedule at the moment. More will come. And this relocation prep for Sydney is something that I'm thinking about. Thinking about pretty hard. Like what stuff to bring, you know, what did I buy? Actually, I haven't gotten any response from something that I did buy. It's okay. I will. Is there anything that I need to do now regarding it? Can I think of anything? Can I? Maybe not. Maybe I can't think of anything. So I can close this then. Oh, Gamma will keep it open, but save bookmarks, close tabs, save bookmarks, close tabs, and we can just close this tab. Is that Todoist? No, it's things 3. So I think this is fine. We'll move this to just keep it, I guess. It's fine. We don't need this to be tagged at a time when it doesn't need to be. So we just know where to go to. Alright, so we can leave it like that then. Today is done then. You know, we planned everything else for the future days. We can mark these off. Cool. Is it on the App Store? Yes, it is. Except it's paid. It's like $150 total for all 3 of the apps that you buy on separately on an iPad, iPhone, Mac. It's separate, which is, yeah, it's too much money to spend on a to-do list app, I will say. But I did it anyway. Yeah, unfortunately, it's the Apple tax. It's good, but I still have some gripes with it. That's why I'm making my own app. GFU? What you mean, bro? Let's see. Would there be anything else here for me? We can close this, or we can keep it open because we'll do it tomorrow. Now this is pretty much the only tab that I have open now. Alright. Now, should I do just one more PR? Might as well. In terms of one more PR, I mean, just looking at GitHub. Because I have a backlog of notifications that I got to go through on here. Thanks for the peeps for following. Okay. So many. Can I go through all of this? Perhaps. Perhaps it's unnecessary. Suppressed by this, for sure. So it can just be done. Oh yeah, by the way, isn't it pretty sick that it looks like I'm on Windows right now, but I'm actually on my Mac. Isn't that just pretty sick? Because look, I'm actually on my Mac, right? But I also got Windows. And that's because of the remote desktop, which is pretty sick. Just wanted to point that out. Upgrade fast API. How do you do an upgrade like this? VM? No, it's not a VM. This is a remote desktop. Now that means I do have a computer